Hello, am I audible? You can just, I can look at your reactions now, unlike the previous. Okay, yes, I see a yes. Okay, I'm starting now. We'll first go through the asymptotic notations, and that will get over in less than 10 minutes. No, not even 10, very, very less than 10 minutes. So, the first thing we're going to go through is just tell me if I am too loud or not too loud. Just let me know. Asymptotic notations basically are big O, big theta, big omega, and then we have this small o as well. So basically, if you have a function f of n, where n is the size of the input and n will always be discrete. You can't have an input size 1.5, 2.5, that's not possible. So your input is always a discrete value and it's always non-negative. So anyway, so n could be a whole number or a natural number. So this is f of n. Let's find uh, let's find another sub function. Let's say I'll call it not like this. Let's say this is g of n, or not g of n. Let us say some constant times g of n. Let's look at another function. Uh, let me use another color. Some random function, and then it goes like this. I'll use different constants. Let's call this some other constant times g of n. Fine. Now you can see that g of n, c1 times g of n is above f of n, and c2 times g of n is below f of n after a certain point. So I'll call this point n naught. Now, with using the same graph, we will be defining big O, big omega, and big theta. We'll see what is that. So f of n belongs to big O of g of n if you satisfy a certain condition. Now, first of all, what is f of n? F of n is a function. Big O of g of n is a class of functions. So a class of functions will have a certain number of functions within itself which satisfy a certain condition. So what is the special condition for this? F of n belongs to big O of g of n if f of n is less than or equal to uh, wait, I'll write the condition at the end. We'll need to define some things. If there exists a constant c which is non-negative such that for all natural numbers greater than n naught, for these two constants, f of n should be less than or equal to c times g of n. So if you satisfy this condition, your f of n will belong to the class big O of g of n. So this is the definition for big O of g of n. The graph is simple. You can look at the graph above. This is big O of g of n. I said there exists one c, so it doesn't have to satisfy for all positive non-negative real numbers. Any c will work out, but it's true for all the values greater than n naught. This is big O of g of n. Now we'll look at big omega of g of n. Big O is like an upper bound. You get an upper bound. It's called an asymptotic upper bound. This condition will basically give you your asymptotic upper bound. Why asymptotic? Because you know what asymptotes are, right? They keep getting closer and closer, but then they never meet. They never intersect. Okay, moving on to the definition of big omega of g of n. What is the condition for that? When will a function belong to a class called big O of omega, big omega of g of n? This is the condition. F of n belongs to big omega of g of n. Now it's just the reverse of big O of n. If there exists some c belonging to R plus, basically if there exists a non-negative real number such that for all natural numbers greater than n naught, f of n is above g of n. So some constant c is there. So the same graph, I'm using the same graph here. If you look at it, f of n is always above g of n, where g of n is multiplied by some constant, some non-negative constant. So that was big O of g of n, and this was big omega of g of n. So here you get lower bounds, upper bounds in the top, and then lower bounds here. So let me write upper. Is this what? Okay. Upper bound. This is lower bound. I mean, all of this is just definitions and words, but you're supposed to understand what's happening. That's why I'm writing upper bound and lower bound. Now we'll look at. If anyone has a doubt, do stop me. I'm just going through the things as fast as possible. Now we look at big theta of g of n. This is also a class of functions. So f of n belongs to big theta. Is this theta? Big theta of g of n if it satisfies some conditions. If there exists c1, yes, if there exists c1 and c2 which are non-negative, such that for all natural numbers greater than n naught, my f of n my f of n lies in between like this. I'll just write it here. C1 times g of n. My f of n lies in between two different functions. One function is c2 times g of n, the other function is c1 times g of n. The function g of n is the same, but then you're simply changing it by multiplying it with a bigger constant and the other time a smaller constant. The graph is the same thing. You can just look at the graph. Here, if you see, g of n is the same function, but then one time it's above f of n, the other time it's below f of n. It is because of the constants c1 and c2. So if f of n satisfies this condition, then f of n is said to belong to the class of big theta of g of n. Basically, the average case. It's like f of n is growing along with g of n. You can think of it like that. It is bounded both above and below. So upper bound and lower bound, but together. So usually O of n. Okay, fine. I'll not get into other things. This is fine. So this is, it is both upper and lower bound together. Fine. So these three are the definitions of big O of g of n, big theta of g of n, and the second case was big omega of g of n. The last asymptotic notation we looked in the class was small o of g of n. That has a slightly different definition. It's not the same as this three, just slight variation. That is also a class of functions. F of n belongs to small o of g of n if some condition is satisfied. Now the condition is, now here look at the condition. In the previous three definitions, it is there exists, but in this for small o we have for all c which are non-negative. So I can simply write for all c greater than 0 or for all c belonging to positive real numbers. There exists some n, or I can say some nc or n naught, you can write whatever, belonging to natural numbers, such that f of n is strictly less than c times g of n. Now, if you compare this definition with big O of g of n, the differences are here you don't have a less than or equal to, you simply have a strictly less than, and the other difference is here it has to be true for all c's. Wait. And yes, it has to be true for all the values greater than NC. This condition is there even in the previous definitions. Now, I mean, why did I have to explicitly state this? Because, I mean, you just look at the examples. That should, you need not think about it much. This is the definition. See, now this is the entire asymptotic notations. If you have any specific doubts, you may ask me. I'll be able to reply. But we won't be dealing with much of these except for the big O of G of n. So that will be our main thing. Not that the others are out of syllabus. Everything is in the syllabus. Fine. This is asymptotic notations. I will be moving to the next topic in 10 seconds. So let's take a 10-second break. I'll just put this like this. I think that's 10 seconds. I did not count anyways. After asymptotic notations, we'll be looking at something called efficient algorithm. Efficient algorithm. There's a definition for this apparently. An algorithm is said to be efficient if there's a condition. So you satisfy, if your algorithm satisfies that condition, it becomes efficient. Now, what is the definition? Let's say n is the size of your input. If n is the size of your input, and if your algorithm runs in, let's say, algo runs in some polynomial of, or let me write polynomial of n. If it runs in polynomial of n time units, this makes your algo efficient. That's it. So I'll give you some examples. So if I have to say this again, if n is this input size, and if your algorithm runs in polynomial of n time units, that means your algorithm is efficient. So for example, if I'll give you some examples in terms of the notations. So if your algorithm is O of 1, 1 is a polynomial of degree 0, it is efficient. O of n, a polynomial of degree 1, it is efficient. Let's say you have something like O of 9999. This is also a polynomial. This is still efficient by definition. So, yes, if there's any algorithm running in O of n power 999,999, it is still efficient by definition. As far as the definition is concerned, this is an efficient algorithm. There is nothing more to efficient algorithm as far as our syllabus is concerned. So I will be moving ahead to the next topic in 10 seconds. So just have a look at this.
Dilip,
Okay, yes, a doubt?
once can you repeat the example? I didn't understand.
Okay. See, algorithm takes some time to work on the input, right? If you give some input, algorithm will work on it. If the size of the input is n, like for example 10 bits or 20 bits or 1 million bits, whatever, if n is the size, in the later classes we saw that we're using t of n and so on, right? Am I audible?
Yeah, I'm
So
listening.
we are trying to represent the time taken by an algorithm in terms of this, right? T of n,
Yeah,
where n is the input size. So the time taken by the algorithm is a function of the input size. That's why we're writing t of n, like f of n, t of n. Now, if this t of n belongs to, for example, O of some polynomial in n, then that algorithm is said to be efficient.
okay, I
That's it.
got it.
Like by definition, you don't have to think much about it. That's it.
Okay.
That is what I'm trying to tell. If your algorithm,
Dilip, can you put that
okay,
in notes?
Okay, this equation, fine.
Yeah, yeah.
Let me just write, because I didn't define T of n yet, right? So that's why. Okay, I'll write it anyways. If I'll write it. If T of n is the time, put a star here, taken by an algorithm to do something. Let me write to do whatever. I'll not write it. If T of n is the time taken by an algorithm, and if T of n belongs to big O of polynomial in n, where n is the input size, then the algorithm is efficient. Then the algorithm is efficient. That's it. This is what I was trying to tell you. That is what I wrote here. If the algorithm runs in polynomial of n time units. Okay, fine. Efficient algorithm is done. After this, we'll be starting divide and conquer. In divide and conquer, we have subtopics. After divide and conquer is done, we will be going to greedy algorithms. Under greedy algorithms, we have some subtopics. After that, everything will be done. So I will be starting greedy algorithms now. Let me put some nice colors. Right, divide and conquer. Divide and okay, let me push this to the left. Divide and conquer. Divide and conquer is basically like you have, let's say, your input size is n. Instead of solving the algorithm, instead of applying the algorithm to solve the problem, you'll divide it into sub problems. For example, you can divide it equally into, let's say you're dividing it into a sub problems. So ideally, it will become n by a, n by a, and so on. So instead of solving this, you'll apply your algorithm on n by a, n by a, n by a, and add all of them. For example, if you remember merge sort, instead of what happens in merge sort, you break the array into halves, right? Left half, right half, left half, right half. Finally, you will get one sized arrays at the end, and one sized arrays are already sorted. Then you will merge these two, then you will keep merging. If you remember merge sort, that is what we did. We are dividing the big problem into smaller sub problems. Later, we are merging all of them together. So I'll not get into much detail, but then we'll see. Divide and conquer is basically taking a big problem and dividing it into smaller subproblems. So master theorem is there. Master theorem will basically help us find out the time complexities of algorithms which use divide and conquer approach. So we look into the master theorem. The first one is master theorem. I will not prove master theorem, and the proof of master theorem is out of syllabus, but it is in the notes. I shared a PDF, right? The proof of master theorem is in the notes. If you want, you can look at it, or else you can always Google it. That is a different story. But as far as the syllabus is concerned, we will look at the question of the master theorem and its answer. There is a question, there is an answer. So the question is this one: if you have an algorithm that runs in t of n time units, and by divide and conquer, what is happening is, let me write the equation, then I'll tell what is happening. A times t of n by b plus o big O of n power d, where a is greater than 1 and b is greater than 1, where you could assume n is, you could assume n is equal to some. This assumption is because my Uh, if I assume this, my n by b becomes simpler. So you could assume this. That is what sir did in class, so that you don't have to worry about the ceil function. It makes our lives easier with this assumption. This assumption is going to make our life easier. So, anyways, now what is this big thing? What is happening here? What is happening here is I have an algorithm. If you input, if you give an input to it, which is of size n, it runs in t of n time. But this is my LHS. Now, what is happening on my RHS? What is happening is I have a times t of something. Now, what is t of something? T of something is the time taken by the algorithm if you give it an input of size ceil of n by b. It means this is our input. The time taken by the algorithm to work on this input is t of ceil n by b, and we are multiplying it with a. It means there are a such sub problems. So basically, what is happening is, let us come back to this diagram before. You have an input of size n. You're dividing it into a sub problems. Ideally, you would think that the size of each sub problem will be n by a, n by a, n by a, and so on. But for the sake of generality, what I'll do is, instead of keeping the size as n by a, I will change it to n by b. Why n by b? I'm making it more general. But you might ask me, shouldn't this be still be n by a and so on? But later, when we look at other problems, you'll realize this b is not always equal to a. So, anyways, size of input n divided into a sub problems, and n by b is the size of each sub problem. Size of each subproblem, or whatever, size of the input of each subproblem, size of input of each sub. Then what is n is our original size of input to the main problem. If the main problem has input size n, it has a subproblems, and each of the subproblems has size n by b. So that is what is happening here. You have a subproblems, and each of the subproblems input size is n by b. The time taken by the algorithm to work on this is t of n by b. There are a such subproblems, so a times t of n by b. Fine, all of this is fine. Now, what is this plus big O of n by d? This plus big O of n by d is there for a reason. The thing is, after you divide it into subproblems, you're supposed to bring all the answers together. So that will require some extra work. For example, in merge sort, after you subdivide everything into left and right arrays, like half, 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 and so on, you're supposed to merge each of them together. So that will take some extra time. That is represented by some big O of n power d, some polynomial. So d something. I mean, it's fine. Some number, O power n by d. D is some number. This is still a polynomial, hopefully. If it's a polynomial, this is efficient. So yes, you can see efficiency. This is the question basically. This is not the answer. We did not solve anything here. You can represent an algorithm, an algorithm's time complexity using this relation. If you're able to express it in this relation, then we can find out the time complexities, upper bound, lower bound, whatever. So there's a solution to this. The master theorem states that if this equation is true, then my t of n will be of the order, it will belong to the class of big O of n log a base b if log a base b is greater than 0 d. It will belong to big O of n power d if d is greater than log a base b. It will belong to big O of n power d log n if d is equal to log a base b. This is the solution to the equation that I just tried to explain to you people about. This is basically the master's theorem. It says that if you have an algorithm which is running in this much time units, which can be expressed as a number of subproblems, you have a number of subproblems into the time taken by the algorithm to solve each of the subproblems of size n by b, plus some extra work done, which is very problem dependent. We look at some problems. The solution is this one. We will see how to use the master theorem in the upcoming examples. Our first example is merge sort, very evergreen example. Merge sort uses divide and conquer. So we will look at merge sort. I'll stay here for like 10 seconds. We'll just let that sink in. Fine, I think that's 10 seconds. We look at merge sort. What happens in merge sort? Let me write merge sort. Merge sort, merge example 1. Merge sort. See, I won't be explaining merge sort. I just draw the diagram. You have some array. Let me use some other color. You have an array, then you break it into two halves. Then you'll get this also. You'll break it into two halves. I mean, you do remember, no? Break, break. You'll use recursion and break everything. Break, break. See, if you look at the diagram, you're realizing, no, this was n. Now its size is n by 2 approximately. You're dividing it into half, and finally this becomes like this. Uh, After you recursively divide everything, then you start merging, merge, merge, and so on. I mean, if you know merge sort, you know what's happening. You keep doing this recursively, and then you start merging. You're merging two sorted arrays. See, fine. This is merge sort. I hope all of you know what merge sort is. Now we are going to use the master theorem to find out the time complexity of merge sort. So what actually happens in merge sort? See, this is this is our main problem. No, you have an array of size n. Size. Use a different color. Sorry. This is an array of size n. Approximately the size of the array that you divided is approximately n by 2. Approximately. This is also approximately n by 2. If you remember recursive relations, do remember recursive relations, right? This master theorem is a recursive relation. Why is it a recursive relation? Because on the LHS I have t of n, on the RHS also I have t of something. I am representing a bigger number using a smaller number. So that is exactly what recursive relation is, right? Even in merge sort you use recursion, so you get the idea, right? So I'm trying to write down the time complexity of merge sort. How do I write the time complexity of merge sort? T of n is the answer. That's it. T of n is the answer. T of n is the time taken by merge sort to sort an array of size n. Now this is equal to something. What is it something? I can recursively write the answer. How can I recursively write the answer? I will first sort this thing. I will sort this thing also. That will take how much time? Sorting n by 2 elements will take me t of n by 2 time. And I'm sorting two such arrays. One is the left half, the other is the right half. So it will take me two time units of n by 2, whatever. So 2 times t of n by 2. This is the time taken by merge sort to sort an array of size n by 2. because by definition T of n is the time taken by merge sort to sort n element array. Is our job done? No, it's not done, because after sorting our two arrays, you're supposed to merge them. If you remember the algorithm of the merge function in merge sort, you'll be able to find its complexity. Now, what does merge do? When you're merging two arrays, when you're merging two arrays in merge function, what you do is you always compare the first elements and then you shift it to a temporary array, right? If you remember, whatever is okay, I'll take an example here. See, okay, fine. I won't take an example. You should. I hope you remember what the merge function is about. You take the smallest value, you put it here, or whichever one is smallest, you strike it off. Then you compare these two. Whichever one is smallest, you put it here. I hope you do remember the merge sort, no? Then you strike that off. Whichever one is smallest next, put it here. Strike that off. So on and so forth. So this will be accomplished in O of big O of n. It is just a linear scan. You just do you people remember the merge function in merge sort, or would you go through it by yourselves? Uh, okay, I'll give a small example. Let's say in the merge function, you'll be merging two sorted arrays. So I'll give a sorted array here: 2, 3, 7, 9, 10. The other sorted array is let's say 1, 2, 3, 4. Okay, fine. These two are sorted arrays. You're supposed to merge these two arrays. Let's see how much time does it take. I'll compare these two. Which one is short? My short is 1, so this is gone. Next 2 and 2. I mean both of them are same, so 2, 2, 3 and 3. 3 is short. You can just take some 3. 3 and 7. 3 is small. 4 and 7. 4 is small. After you exhaust one array, you will simply copy all the other elements. So this will directly be 7, 9, 10. This is what happens. So in merge function, this is how you merge two sorted arrays. The size of each array is approximately n by 2, because we just saw right. This is approximately n by 2. I mean, not in the example, but in the merge sort. Okay, let me make it n by 2. Now it is approximately n by 2. The size of this is also n by 2. We are traversing each element once, so it is equivalent to traversing an array of size n. That means this merge function will, it is of the order of big O of n. You do get the point, right? Array traversal is big O of n, because you're you're passing through each element once. Size is n, because n by 2 plus n by 2 is n. So the extra work done by merge is this much, big O of n. What we just did now by writing this is writing the recursive relation. After you write this, you're supposed to solve this using the master's theorem. Now, how do we? Sorry for the background noise. Anyways, so how do we solve this? Is you apply the master's theorem. Now, let's see how do we apply master's theorem. Uh, master's theorem. Master's theorem. No, let me write this here. Just substitute. A is 2, B is also 2, D is 1. Log A base B. How much is that? Log 2 base 2. How much is that? 0. 0, right? Is it 0? No, it's 1. This is 1. Log 2 base 2 is 1, which is equal to D. So, using the Master's theorem, when we have log A base B equal to D, what are we supposed to do? our time complexity is going to be big O of n power d log n. So I can directly write by Master's theorem T of n belongs to big O of n power d log n, which is nothing, d is 1 here, so big O of n log n. Hence merge sort is of time complexity big O of n log n. This is how we use master theorem for algorithms which use divide and conquer method. Nice. Now I don't think I should be spending much time explaining things. I'll just be getting faster, hopefully. The other example in the notes was about addition of two n-bit integers. If you have any doubts too, let me know. Like what is this A, B, D? We just looked into it previously. A is the number of subproblems. Or just look at this. This is our A, this is our B, D is over here. That is how, compare it with the master theorem thing, then you will get your solution. If your questions are something like what is A, what is B, essentially, I just told it to you before. A is the number of subproblems. N by B is the size of each subproblem. So time taken by each subproblem is T of N by B. The extra work is accounted for by adding a plus big O of N power T. Next example was addition of two n-bit integers. Now we are supposed to find out the time complexity of adding two n-bit integers. I mean, if you have two n-bit integers, fine. Now let me take an example. 1 1 0 1 0 0. You have to consider that if you're adding two bits, that is one time unit. So 1 bit plus 1 bit. This is the addition. Your computer does the addition in one time unit. This bitwise addition, whatever it is, 1 bit plus 1 bit, that takes one time units. So if you're adding two bits, you will take one time unit. So how much does this take? 0 plus 0 is 0, one time unit done. 1 plus 0 is 1, that is also one time unit. 1 plus 1 is 1 1, that is also one time unit. So this problem took 3 time units because you performed 3 additions. You took 3 time units. So can I say something in general for two n-bit integers? We are supposed to look into it, but let's see. What about this example? 1 1 1 1 1 1. 1 plus 1 is 1 1, one time unit. But now we have 3 digits. You don't have 2 digits. So you need to perform 2 additions. 1 plus 1 is 1 1. 1 plus 1 is, sorry, 1 plus 1 is 1 0. 1 plus 1 is 1 0. 1 plus 1 is still one time units. 1 plus 1 is 1 0, one time unit. 1 0 plus 1 is 1 1, that is one time unit. Same thing. So 1 plus 1 is 1 0, 1 0 plus 1 is 1 1. We had how many time units there? 1, 2, 3, 4, 5. Here you got 5 time units. Now I have to find a general case and I should be able to tell how many time units is this going to take. Okay, there's a mistake here. No, 1 0 plus 0 is this one. 1 plus 0 is 1. 1 plus 1 is 1 0. Yes. Nice. Uh, Fine. Now I have to find. Okay, what I'll do is, big O of anything will represent my upper bound. So to get the upper bound, I'll take the worst case possible. I am not telling big O of n always represents worst case. I'm telling that to get my big O of n, I will assume the worst case possible so that I will be able to estimate or approximate what my worst case is. So what is my worst case in adding two n-bit integers? My worst case is when I have all ones. The problem is when I have ones, some digits are getting carry forwarded, and that is contributing to more additions. Previously, I simply had one addition here, one addition here, one addition here. Here I have one addition. In other places, I have two additions. So if I have an n-bit integer, 1, 2, 3, and so on. If I have two n-bit integers, let's say this is n minus 1, this is 1, 2. If I add the uh, if I add these two digits, I will always get one addition, so that will take one time unit. If I add any other digits in other places, there is a possibility that I might have gotten a carryover. So I can say that in the worst possible case, for all my n minus 1 bits, there will be a carry forward. So that will be like around two additions. You get two additions. For example, here you've seen, no, the previous case, except the first place, all the other places got two additions. So I can say it is 2 times of n minus 1. I am performing 2 times of n minus 1 additions. So in total, it is like 2n minus 1 plus 1 is 2n minus 2 plus 1, which is 2n minus 1. So in the worst possible case, I will have to perform 2n minus 1 additions, but no more than this. It is either equal to this or less than this. So I can simply say that my time complexity of adding two n-bit integers is of the order of n. This is the conclusion. Now, some of you might get a doubt. See, if I'm adding three digits here, you're telling that one digit will come here and one carry forward will come here. What if I get two carry forwards? Is that possible? Then you'll get more additions, no? But the thing is, there is a proof, not there's a statement which has a proof, which I gave in the notes. The sum of three digits, not numbers, the sum of three digits of any base has at most two digits. So, for example, if you take base 2 and if you add the three biggest digits, which is 1, so 1 plus 1 plus 1 is 1 1. It has two digits. If you take base 10, 9 plus 9 plus 9 is 27. You take any base 100, base 16, anything you take. If you add three digits, your final answer will never cross two digits in that base, in that numeral system. The proof I gave it in the notes, you can just see. It is not, I will not say not required, just go through it, but I'll not tell it here. It's simple, it's quite a simple proof, you can just go through it. So this ensures that whenever a carry forward is happening, the carry forward is either one digit or there is no carry forward, zero digits. I won't have a carry forward that has two digits. So it is, this calculation is correct. At most, you'll get 2n minus 1 additions. The next example is multiplication of two n-bit integers. How much time does that take? I'll simply write mul, mul, multiplication of two n-bit integers. I'll just not write, okay, fine, let me write multiplication of two n-bit integers. Now we're supposed to find out the time complexity of this one. Now what is multiplication? Multiplication is just addition, but addition more number of times. For example, let's see, if you're multiplying 110 into 11, what happens? 1 into 0 is 0, 1 into 1 is 1, 1 into 1 is 1. Next, you'll leave this place. 1 into 0 is 0, 1 into 1 is 1, 1 into 1 is 1. You're adding two numbers here, that's it. Multiplication is addition. Let me take another example. Uh, okay, let's see. 11010, you leave this 11010, you leave this 1100. This is also, see, it's simply addition. Multiplication is just repeated addition. I know that my addition takes O of n, big O of n time complexity. Now I can easily say how much my multiplication takes. How much is it? Let's say Adding these two numbers is big O of n, like around n. We are not, we are least bothered about the exact number of additions, because finally all constants, like anything, if you let's say 999 n plus 223, this is also simply O of n, so I don't have to exactly find out the coefficients and constants. You don't have to exactly find out the number of additions. That is not our purpose here. So approximately the number of numbers you're going to get here. How many numbers will you get? Approximately. Let me just see. That is of the order of n, I suppose. Let me look at another example and just verify. Here I got two numbers. Here I got three numbers. If I take a bigger number, what will happen? Okay, both of them are of size n, no? So I have to take of the same size. So I'll put zeros. 2 is not a binary number. So what will this be? 1 1 1 0 1. 1 1 1 0 1 1 1 1 1 1 0 1 0 0 0 0. Okay, so how many ever digits are there? Those many numbers I'm getting, because both of them are supposed to be of size n, equal size. That is what the question is asking. No? Two integers of size n. So I'm getting n numbers. This means I should perform n minus 1 additions, because see, plus sign comes only 4 times. 1, 2, 3, 4. Each addition is of order of n, and I'm performing addition n minus 1 times. So this will be of the order of n square. Because I'm doing an addition n minus 1 times. Each addition takes around 2n minus 1. No, I'm least bothered about 2n minus 1. I can simply say n. N into n minus 1 is the order of n square. So multiplication is order of, big O of n square. I don't think there is much to think about this. This was the third example. These examples are for using the master zero. No, they're just there for. They're just there. We'll look into why this is there. Why is this there? I don't know. Okay, fine. Maybe it's just there to familiarize with you, familiarize you with writing asymptotic notations. The, okay, this is the fourth example. The fourth example says binary search. What is binary search? Let's say you have an array. Let me write binary search. Binary search. I am not okay. Even if I say I'm not explaining binary search, it's going to be binary search. Binary search. Binary search. Okay, you have an array. Uh, where is binary search used? Is that used on a sorted array or a tree or something? I don't know. Binary search is, let's say you start. Let's say you have a sorted array. Is it a sorted array tree? Binary search tree lo untundi kada? It's a tree. So I have a binary tree. That's okay. Binary search because it's a binary tree. So I have a tree, whatever it is, some random tree. I can represent a binary tree using an array also. Fine. Anyways, and let's say whatever is on the left is less, and whatever is on the right is more. So let's say I have 10. This is 5 to 7. I have 20. I have 15. I have 30. I hope this is a correct binary tree. But let's get on with this. Let's say these are binary search. Let's say you want to search where is 15. How do I search where is 15? First, I'll start here. I'll see if 15 is smaller than 10. It's not smaller, so I will go here. Now, using divide and conquer, what I'll do is I have to find the time complexity of binary search, right? Let's say the size is n, so the time taken by binary search will be t of n. If I have an array of size n, which represents a binary tree, the time taken by binary search is t of n. Now, if I perform the first comparison, I can simply discard the other half. After performing the first comparison, let's say I'm searching for 15, search 15, search 15. I'm discarding the first half of the tree. So that means my subproblem is now just go through the right tree, right subtree. So that will just be t of n by 2. Let me see if the meeting is getting recorded. Let me just verify. Yes, it's getting recorded. Anyways. Okay, fine. So T of n is the time taken by binary search to search through the entire tree. After making the first comparison, which will take like 1 or simply O of 1, I have to search through the other half of the binary tree. So this is my recurrence relation. Using the master's theorem, I can find out the time complexity of binary search. So A is, see, the problem will be given. You're supposed to know how to write the recurrence relation and then how to use the master's theorem to find out the time complexity, especially for divide and conquer algorithms. This is a divide and conquer algorithm. A is 1, B is 2, D is 0 because n power 0 will become 1. So log A base B is log 1 base 2, which is nothing but log 1 in the car, because you're making one comparison. Eight equation. A is here, B is here, D is over there. 1 is nothing but fine. So log this is 2 power 0, right? 2 power 0 is 1. So this is 0. 0 is equal to 0. So my T of n belongs to big O of n power d log n. That is what the master theorem says. My d is 0. So this is basically big O of log n. So binary search time complexity is big O of log n. That is all there is to the time complexity of binary search. Now comes one of the main subtopics: multiplication of two n-bit integers using some new algorithm. We'll be using a new algorithm and we'll be checking the time complexity of that algorithm. We just saw previously that multiplication of two n-bit integers is of the order of n square, and this algorithm tries to make it better. It wants to decrease, it wants to like something better than O of n square. So let's see what is that algorithm about. uh, Multiplication, if someone has a doubt you can just ask me. Right, multiplication of two n-bit integers, but better. Let's see what it is, and we'll be featuring Gauss. Right, it feels nice to write it this way. We'll find Gauss. He'll come from somewhere. He'll tell us how to do this. Is it Gauss? Yes, it's Gauss. And yes, we have some complex numbers as well, featuring complex numbers. But I mean, there's nothing much to fear about. I'll just tell you why I'm writing these two things. Okay, we'll get into the algorithm. Let's say you have x and y, two n-bit integers. Uh, since they're n-bit integers, n bits, I will try to represent x and y using bits. So instead of writing ones and zeros, I generally write them as xn, xn minus 1, xn minus 2, so on till x2, x1. So this is the binary representation where each xi is either a 1 or a 0. You don't know what it is, so I'm just writing in terms of x. And the y is represented similarly. You have yn minus 1, yn minus 2, and so on until y2, y1. So mathematically, my x, the value of x is what is it? 2 power 0 into x1 plus 2 power 1 into x2, so on, 2 power n minus 1 into xn. So you do understand, right, why all of this is happening. This is the least significant bit and this is the most significant bit. So least significant bit is like 2 power 0th place to, anyways, I think all of you know this. So I can simply write this as summation 2 power I x, or 2 power I minus 1 xi. I is ranging from 1 to n. This is the value of x, this is the representation of x, so both of them are different things. That's why I used an arrow mark here and I used an equality sign here. So representation is different from the value. Fine. So y is also the same thing. So y is summation 2 power I minus 1 yi. If anyone's feeling like overloaded by looking at all these equations, do let me know. I mean, there's fine. I'm not commenting on this. To make our lives easier, we are making an assumption. We assume that n is some power of n is a power of 2, some power of 2. To make our lives easier, you can not assume it and still proceed, but to make our lives easier, we'll assume this. So what I'll be doing is uh, this x is there, no? X is basically, let me use a different color here. X is xn, the representation. So the bits are xn, xn minus 1, xn minus 2, so on. X n by 2, x n by 2. Since I assume that n is a power of 2, n is an even number. So n by 2 is a valid index. It's not invalid because I can't have x 1.5. No, that makes no sense. So that's why I had to assume this. If you don't assume this, then you will be dealing with seals and floors and whatnot. So I'm not going through that. So x2, x1, fine. Now what I'll do with this is I will divide and conquer. No, so I'll be dividing this. I'll divide this right in between, and I will call this XL. I will call this XR to get an idea as to what I'm doing. Let's say you have some 4,987. This is some number in decimal number system. What I'm doing is I'm dividing this right in between. I'm taking this number 49. I'm taking this number 87. This is what I'm doing to my x, the number x here. I don't. So the same thing I'll be doing with my y. So XL is represented using. Let me change the color. XL representation is this one, xn minus and so on till xn by 2. Okay, anyways, the value of xl will be, since this is the least significant bit, you have to sum it up. 2 power I minus 1 xi I starting from n by 2. 1 minute, I'll just be back in 10 seconds. I am back. Okay, fine. So summation I starts from n by 2, it goes on till, where does it go to? N. This is the value of xl. But beware, my x is not mathematically equal to xl plus xr. This is wrong because I gave you an example. No? When you take 4,987 and when you divide it into half, 4,987 is not equal to 49 plus 87. Be careful. You have to multiply 49 with what is it? 100? 100, yes. Then it will become equal. So you can't simply say this. You have to multiply XL with something. we'll look into what it is. So Excel is this one. Uh, XR you can write, YL you can write, YR also you can write. All of that you can do. It's in the notes. You can look at the notes. This is the idea. Now, how do I write X using in terms of XL and XR? X is basically what is it? I wrote XL here, no? I mean X. This is the value of X. I'll write it again. 2 power 0 into x1 plus 2 power 1 x2, so on till, let me stop in between, 2 power, if this is xn by 2, this is xn by 2 minus 1 plus 2 power n by 2 xn by 2 plus 1 plus 2 power, and this goes on, 2 power n minus 1 xn. If you notice, if you paid attention, if you notice, this is nothing but the exact value of x. What is this supposed to be? This is supposed to be my xr. This is my xr, exact value, not representing, exact value of xr. Now this is not excel, be careful, this is not excel. This will become, because you do know, no, my x is not equal to xr plus xl, because if you believe that is true, then 49,087 is nothing but 49 plus 87, which is false. So let me write this as xr. To get my xl, what I'm supposed to do is I'll take 2 power n by 2 common. What I'll get is x n by 2 plus 1 plus so on till 2 power, what is this going to be, 2 power n by 2 minus 1 xn. If you notice, xl is the same as whatever is inside this. If you notice carefully, I hope you do notice it. Is it the same? xl, oh, did I miss something? No, the division is slightly off. I need to start it from xn by 2 plus 1. I am dividing it from here. Sorry, this is the right division. So, yes, so slightly off by one digit, but it's fine. Yes, now it's correct. I wonder why did no one correct me. Anyways, is no one uh, on the same page with me? We are on the same page. See, this is the same page. Anyways, uh, I hope that's true, at least in theory. So I got my XL. So I represented X in terms of XR and XL. This is the extra value. Now these two are exactly equal. Even Y are, I mean, Y can be represented in the same way. I mean, if you do not understand what's happening, just go through the notes. It's the same thing. I'm not copying it. I'm trying to write it once again. Fine. So I have X represented in terms of XR and XL. I have Y represented in terms of YR and YL. Why are we doing all this? Think about the main question. The main question is use divide and conquer somehow. What I'm trying to do is I'm trying to divide my X in terms of XL and XR and trying to apply my algorithm on that. We'll see what it Gauss do. I don't know, featuring Gauss and so on. Let's see. Now I want the product of X and Y. I want X into Y. Since I represented X in terms of its XL and XR and so on, I'll just write that. So X is XR plus 2 power this one into YR plus 2 power n by 2 YL. This is finally, if you simplify this, you'll get something like 2 power n XL YL plus 2 power n by 2 XL Y XL. You just have to simplify this because, okay, X is, just put a dot here so that you don't get confused. XRYL. Okay, time is 5. Okay, 4. Okay, fine. Anyways, you should fasten things. Speed, not fasten, speed. Fasten is doing something else. Slow and this is faster. The derivations are remember. Fine, this is the product of X and Y in terms of XL, YL, XR, and YR. Now, what do I gain with all this? The thing is, here X and Y, each of them is of size n, but XL, YL, each of them, XR, YR, XL, YL, they're of size n by 2. So, if there is any algorithm multiplying two n-bit integers, let's say it takes t of n time. What should I change the color? Okay, I'll change the color. If there is any algorithm multiplying two n-bit integers, and let's say it takes t of n time, is there any benefit that I get by just multiplying these numbers XLYL, XLYR, XRYL, and XRYR? Here I'm performing four multiplications, but each of them has numbers of size n by 2. So the time taken by each of those multiplications is t of n by 2. I have four such multiplications, so four subproblems basically. The size of, okay, multiplying two n-bit integers will take t of n time. Multiplying two n by 2 bit integers will take t of n by 2 times. I have four such multiplications, so it's 4 times t of n by 2. Is our job done? No, it's not done. You might have questions as to what about this multiplication? I still have to multiply it with 2 power n by 2. The good news is multiplying or dividing with the powers of 2 is just left shifting or right shifting, so that is not much of a problem. You do remember left shift and right shift, right? If I have a number 1, if I left shift it once, it becomes 1 0. If I left shift it twice, it becomes 1 0 0. This will not take much time. There's no multiplication involved. You're just left shifting and right shifting. So that will not contribute to my multiplication problem. You can think of it as O of 1 or O of n. That is not a problem. Now. After you perform these four multiplications, you're supposed to, even after the left shiftings, you're supposed to add them. How many numbers are you adding? You're adding one, let's say this is one, two, three, four. You're adding four numbers. Adding four numbers means you need to perform three additions, and addition is of the order of n. We just saw previously. Okay, this is where we are using the previous result. Adding n-bit integers is O of n. Is it O of n? Yes. You can write, see, the size is n by 2, but constants are ignored, so I can simply write O of n. I am adding integers of size, I don't know, it could be anything. After you multiply, the size will change, no? So, but they'll be of the order of n. Some constant times n plus some constant. Anyways, if you do get the idea, this is the final recurrence relation associated with whatever we did just now. I don't think we have a name for that, at least. I think there is a name, but we are not aware of what the name is. Apply Master's theorem and let's see if it does better than big O of n square. If you apply Master's theorem, you'll get A is 4, B is 2, D is 1. Log A base B is nothing but log 4 base 2, which is nothing but 2. 2 is greater than D. So my T of n belongs to big O of n log A base B, which is unfortunately O of n square. All this nonsense we did, and we still get O of n square. Where is the better way? This is where Gauss comes in. Gauss comes in, he tells that you don't have to do four multiplications, which we did here. He shows us a method in which we can just use three multiplications. And if you use three multiplications, this four will become three, and your answer will become better. Now, how do we use the three multiplications? The idea behind that is it comes from complex numbers. In complex numbers, what Gauss did was while multiplying two complex numbers, the solution to this is basically What is the solution? AC minus BD plus I times AD plus BC. This is the solution. Here you're getting four multiplications. So what Gauss did was he tried to simplify it and bring it down to three multiplications. How he did that was he introduced some constants. So he defined some products he defined. So P1 he defined it to be mm, AC, or P2 he defined it to be BD, P3 he defined it to be not this one, A plus this number into this number. Now, what is it mathematically? You'll get AB plus DB plus DB, DB plus DC, AC or AC ले लेना AC AB plus AC, DB plus DC. Okay, yes. This is mathematics. Okay, fine. So here I have one multiplication, one multiplication. Here I have one multiplication. Here also I have one multiplication. You have extra addition, but addition is not a problem. It is O of n. So I'm increasing my additions, but I decreased my multiplication, which is costlier. Now the thing is, how is this P1, P2, P3 related to this? Because my final solution is basically uh, P1 minus P2 plus I times uh, P3 minus P1 minus P2. I simply used three multiplications, but I increased my number of additions. That is not a problem. Addition is of the order of n. We looked at it previously, but multiplication is expensive, order of n square. So I decreased it. This is what Gauss did for his complex numbers. We will use the same trick and reduce our number of multiplications. So instead of doing all this, I will define new products. So I will my P1 for this case is I mean it's in the notes. You can look at it, right? Uh, I will define my new P1. It is XR My P2 is XL My P3 is XL plus. I mean it's alternating into XR plus YL. If you want, you can subtract it here as well. I mean, to make the final equation simpler, I'm just subtracting it here itself. P2, not P3.
తెలియకను XL plus XR అని రాశారు. XY కాదు X and XR.
Okay, X and XR. Okay, fine. This is apparently the same thing. Okay. X, Y. Okay, yes, this was the product. The final answer, X into Y, is simply 2 power np2 plus 2 power n by 2 p3 plus p1. Using this whatever approach I did here, I only used three multiplications but more number of additions. That is not a problem. That is order of n. So using this approach, let us find out the time complexity. How do I get this? You simplify. You just try simplifying and see. You will get the same answer. I'm least bothered about the derivations. You don't have to by heart it or something. You can look at it yourself. You can just open everything up and see. You can explore stuff, right? Anyways, T of n, uh, I am using only three multiplications. One it is here, multiplication 1, 2 and 3. Additions we'll look into it later. Three multiplications, each is of the size n by 2. So multiplication algorithm will take time T of n by 2 time units. The extra work done is addition. Subtraction is simply addition. So I'm adding, I don't know, let's say I'm adding some number of numbers. that is still a constant. I'm adding a constant number of numbers. That will still be O of n. Because precisely, I am least bothered about the precise number of additions I'm performing. Because see, I'm adding how many numbers? One, see, two additions here. Here, one more. So four additions. So four addition means 4n. 4n is usually, not usually, 4n is like big O of n. So I'm least bothered about the exact number of additions. Upper bound is O of n. So, anyways, master theorem, A is 3, B is 2, D is 1. Log A base B is log 3 base 2. I don't know what this number is. I can write one as 2 log 2 base 2. So I can say that this is greater than D, right? Yes, because log is an increasing function. So this means that T of n belongs to big O of n power log A base B using master theorem. This is big O of n power log 3 base 2. This is better than O of n square because uh, what is n? Let's say O of n square is nothing but O of n log 4 base 2. This is better than this. The algorithm which we use now is better than the previous algorithm, which was adding up. We looked at it before, no? Simply adding up all the numbers, our usual multiplication. Our job is done here. This is the analysis, the time complexity analysis of an algorithm. Maybe I don't know. Do you call it the Gauss algorithm? I don't know. Whatever it is, we uh, we featured complex numbers. We featured our mathematician Gauss. Nice. He found a nice method. It's better. Our job is done here. This was the first main subtopic of divide and conquer. The other main subtopic is matrix multiplication of two n by n matrices. I will be going through that in the next 10 seconds. I'll just leave the solution here, the master's theorem. Where's the solution? It's here. Okay, yes. Okay, 10 seconds. Okay, we'll just wait for a while. Next is okay, is it okay? Matrix multiplication. The size of each matrix is n by n, so matrix multiplication of 2 n by n. That's it. A matrix multiplication of 2 n by n matrices. We'll apply divide and conquer here. So let's suppose I have a matrix. I'll give it some names. X. X is a matrix of size n by n. What I'll do is I'll now subdivide this matrix into four submatrices. How do I do that? I'll just draw a plus sign like this. I'm assuming I'm assuming that my n is a very nice number that allows me to do this. If it's not a very nice number, I'm least bothered about it. It can go fix itself. I'll name the submatrices as A, B, C, D. See, for example, if I have a matrix which looks like this: 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So I'm subdividing it like this. So this is my matrix A, this is my matrix B, and so on, something like that. So it can contain any number. Any number. Matrices can have any numbers. Fine. So what is the size of each of my submatrices? The size of my the number of elements in my matrix is n square. I have n square elements in my n by n matrices. Since I subdivided it into four submatrices, each of my submatrices will have n square by 4 elements. So the size of each submatrix is n by 2 into n by 2. You can verify it. It's the same for every matrix. I have another matrix. I'll divide it into another four submatrices, and I'll give it names: A, B, C, D, E, F, G, H. Nice. Now, if you multiply these two matrices, think of these submatrices as numbers and apply your matrix knowledge. How do you multiply these two things? If you multiply these two matrices, you'll get another matrix. So, what will you get? You'll get something. No? A into E plus B, G, A, F. You do remember matrix multiplication, right? It goes like this, it goes like this. I'm not teaching you matrix multiplication. Uh, I'm simply writing the solution. Fine. The usual way you do is if you have, see, there's nothing much to be told here. You have a matrix of two matrices of size n by n. You're trying to multiply them. Let's say the time taken by multiplication is t of n. Since I subdivided it into sub matrices and I'm trying to multiply them, how many multiplications are there? I have one, or let's say 1, 2, 3, 4, 5, 6, 7, 8. I have 8 multiplications, 8 matrix multiplications. And the size of each matrix is n by 2 into n by 2. So the time taken by each multiplication is t of n by 2. Because by definition, if the matrix size is n into n, it will take this much time. If the matrix size is n by 2 into n by 2, this much time it will take. How many such multiplications I'm doing? I'm doing 8 such multiplications. Is my job done? No, it's not done because I have to add my matrices. We did not look at the time complexity of addition of two matrices, so we'll look into it right away. I'll do it here. If I have a matrix of size n into n, if I'm adding it with another matrix of size n into n, I am supposed to add every aij element with bij element in this. Each addition will take each addition will take order of n. So, and how many such elements I have? I have to add n square elements. Left side n square elements, right side n square elements. So total, how many elements do I have in my matrix? How many? N square. So I'm adding n square elements. So total time is like each addition is O of n. I have n square elements. So n into n square is n cube. So if you're adding two matrices, it's of the order of n cube. N is the size of each. You get the point, right? Am I making a mistake? N square? No, not sure. Mm, Can someone enlighten me? Is it n cube or n square? The note says it's n square. Mm, Okay, for the time, I'll just continue. I'll get back to this later. Let me just highlight this. For the time being, let's assume the it is n square. But why is it n square? I do get it. I At one point I did realize it's n square, but I don't remember. Can't remember correctly why is it n square. Fine. I'll just move on. Just I'll come back to this later. Let me put some mark here. Come back later. Fine. I'll come back to this. But apparently the addition of two matrices. I'll tell you later why. I'll put a WhatsApp message explaining why. I'll just put a picture. Addition of two matrices is apparently order of n square. So let's apply Master's theorem and see what is happening. A is 8, B is 2, D is also 2. So log a base b is 3. Log 8 base 2 is 3, which is greater than d. So t of n belongs to O of n power log a base b, which is big O of n cube. So apparently multiplication of two matrices of size n into n is order of n cube. Using divide and conquer, can we do better? Can we perform better than this algorithm? Here comes our beloved mathematician Strassen. He's a German person, so Strassen. So I'll write his name here. He gave us an algorithm. What he says is, in the previous question, in the previous problem, Gauss reduced the multiplications by 1. No? From 4 multiplications, he brought it down to 3 multiplications. This Strassen person, he did the same thing. From 8 multiplications, he brought it down to 7 multiplications. How is it possible? He defined 7 new constants, not constants, 7 new matrices. He named them M1, M2, so on till M7. What are M1, M2, M7? They're all in the notes. For example, M1 is defined to be A plus D into E plus H. M2 is C plus D into E, and so on. M7 is B minus D into G plus H. I did tell you what my A, B, C, D, E, F, G, H's are. They're all the submatrices. I defined them here. If you look into the notes, in all these M7 matrices, we will only use 7 multiplications.
असली notes नहीं.
Uh, as to how did Stassen land on these things, like how did he come up with this? No one knows. There's no proof, but it works. He somehow came up with all these additions and multiplications. He brought it down to 7 multiplications and it works. I'm not going to verify it. If you have free time, probably you can just multiply each one of them and see what's going to happen. After defining them, now what is the final answer? The final answer will be in terms of m1, m2, so on till m7. So what he told was x into y is basically m1 plus m4 minus m5 plus m7. Let me write it. Is there place? Decrease the size. Here you have m3 plus m5. Here m2 plus m4. Here m1 minus m2 plus m3 plus m6. In case I made a mistake, I would like you people to apologize me. But then, everything is in the notes. You can just see. There's no proof for this. They won't ask you in the exam. But this is if do you have to remember the order means maybe it's better, no, you just have 7 matrices, you could probably remember the order. I'm not sure if they'll ask you to write this down, but since it was taught in class, you better just remember it's just letters, right? Okay, fine. Time complexity analysis. T of n, previously it was 8 multiplications. If you simplify this, you will get your answer, which is this one. If you simplify this one, you will get AE plus BG. If you simplify this, you will get AF plus BH. You'll get the same things. So Starsen defined these matrices in such a way that you'll get your final answer with less number of multiplications. The proof is out of bounds, out of syllabus. Anyways, time complexity. Since he reduced it to 7 multiplications, just go through it. Each mi has one multiplication. We have 7 mi's, so 7 times size of each. Okay, let's look at the size. Each submatrix is of the size n by 2 into n by 2. If you add two such matrices, the size is still n by 2 into n by 2. So finally, I'm multiplying two matrices of sizes n by 2 into n by 2. Time taken for that thing, such a thing to happen is t of n by 2. Extra work. What is the extra work I'm doing? I'm adding and subtracting, irrespective of how many times I'm adding and subtracting. Since it's constant number of times, it is apparently O of n square. I will get back to you as to why it is O of n square. But addition of two matrices of size n is O of n square. Now you might think I'm adding two matrices of the size n by 2 into n by 2. No, why is it O of n square? Because if you add this one, you'll get O of n square by 4. O of n square by 4 is essentially O of n square. The constants are ignored. All the coefficients of n square are ignored. So that's why I'm simply writing O of n square. I'm not writing O of n square by 4 because it is not necessary. I can simply write O of n square by 4. O of n square. Can ignore the 4. So time complexity analysis. Master theorem A is 7, B is 2, D is also 2. Log A base B. What is it? Log 7 base 2. What is 2? 2 is nothing but log 4 base 2. So I can directly see that log this one is greater than this. So my T of n will belong to O of n log A base B, which is nothing but previously we got n cube, right? So which one is better? How do we know that? How do I say? Yes. So I know that log 27 is less than two log 8 base 2. So this is nothing but log 7 base 2 is less than 3. So we are performing better than the previously big O of n cube. Before we got big O of n cube, we are performing better than that. So Strasson's algorithm is giving us a better approach. I'm not saying this is the best one. I'm simply saying it's a better approach. This course is only for finding out better approaches, not the best ones. This is all there is to Starson's algorithm, the second main subtopic under divide and conquer. The okay, we have other subtopics. The other two subtopics are finding the median and finding the kth smallest element and closest pair problems. 5 minutes break. I'll give you a 2 minute break. I'll start at 4:50. I'll just be right back. I'll come back by 4:50. 4:50. Oh, sorry, 4:40. I am sorry. 4:40. 2 minutes, right? 4:40.
చాలా స్లోగా ఉంది కట్ చేసిన తర్వాత మానే 6 పేజీలు 2 గంటలు పట్టిందిరా.
It is 4:40. Yes, I will be beginning the next problem, which is which example was it again? This was sixth, right? Sixth, the seventh one. Time to get a bit fast. Seventh one. The seventh one was is about finding the kth smallest element in an array. This you could use this. You could use the solution of this problem to find the median. Median is just the n by 2th smallest element. So in general, kth smallest element. So I'll be trying to find the kth smallest element. One way to do is, okay, I'll just write it. Finding kth smallest element. One way to do is simply sort the entire array, which is of size n. And the best way to sort an array will take time complexity big O of n log n. N log n will be the time complexity. Why is that the time complexity? I mean, uh, I'm not proving it. You can just go through it. But the best sorting, I wrote it down in the notes. The best time complexity, the time complexity of the best sorting algorithm is usually big O of n log n. So sort all the elements. Simply do array traversal. Just write a of k minus 1 after sorting. This will take O of 1 time. So let me write that here. One way to do is sort in O of n log n. Do array traversal. Array of k minus 1. If the array starts from 0, this will take O of 1 time. Array traversal is constant. Just going there. So total time complexity is big O of n log n. Finding the kth smallest element, big O of n log n. The question is, can we do better? I mean, by this time you must have known we'll use divide and conquer. This is the seventh example for divide and conquer. There's an algorithm. I don't think there's a name for it, but we'll just go through it. This is one way, no? We'll go to the other way, the better way. The better way is here. Hmm. What is a better way? Fine. So let's say you have an array. You have an array capital A, and then you have to find the kth smallest element. Let me name the function. Let me call it. Let's say, or let me just call it f. You give it the array, and then you want to find k kth smallest element in array A. This is the array. This is what you want to find. Find kth smallest element. This is the function that is doing the work for you. So we have to find the time complexity of this function. Now, what is the inner workings of this function? We'll be looking at it. What it says is you randomly pick an element from the array, call it m. You randomly pick it m. You can call it whatever. You can call it the pivot element, whatever it is. You randomly pick it, random. And what you do is you create three boxes, three containers. You can call it some left container, some m container, some right container. So left container, right container. I'm calling it an m container for some reason, which you'll get to know in a while. So what you do is after you randomly picked your element m from the array, put it in this container. So m. I made three containers: SL, SM, SR. I'm calling it SM because I am storing my m in that container. Anyways, so after you make these three containers, what are you supposed to do? Okay, how much time does it take to make this container? You can simply declare new arrays. It's fine. We'll come to the analysis part later. We'll just look into the algorithm. After you do this, traverse through the array A, and while you traverse, make a comparison. If it is lesser than m, put it in SL. If it is equal to m, put it in SM. If it is greater than m, put it in SR. So this traversal will take order of n time, because traversing an array is order of n. Randomly picking is like constant time. You can just randomly pick one element m. So after you do that, what will happen? You will get yourself an array. I mean, three arrays, three subarrays: SL, SM, SR. You will have many elements here. You'll have m, all all numbers equal to m. You'll have many other numbers, SR. They are not sorted. You're not sorting them. You're just dividing them. Now, how do I find the kth smallest element? We look at cases. Case 1. If the size of SL is greater than or equal to k, I know for sure that my kth smallest element will be in SL. Why? You ask why? Because I know that all the elements in SL are smaller than all the elements in SM and SR. All the elements in SM are smaller than all the elements in SR. All the elements in SR, I mean, they're not lesser than anything, but all the elements in SR are greater than all the previous values. But within each SL, SM, and SR, there need not be any ordering. These are not sorted elements. We are not sorting anything. We are randomly placing them in SL, SM, SR. But by the property of each of these containers, uh, all the elements in SL are lesser than the values in SM and SR. All the elements in SM are lesser than the values in SR, and so on. It's fine. So why does this imply that the kth smallest element is an SL? Because just think about it. I mean, it's supposed to be obvious. You can't have the kth smallest element. Okay, if you take an, I don't want to take examples. Examples is going to take some time. For example, if you just have a random array 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say I randomly pick 6, 6. Okay, 6. So if I make the containers, 6 is here. I'll traverse through the array. 8 is greater, 5 is smaller, 4 is 4 is smaller, 3 is smaller, 1 is smaller, 2 is smaller, 7 is smaller, 9 is 1. If you look at it, the elements in each of the arrays are not sorted, but I know that all these numbers are lesser than the numbers on the right. All this number is greater than the left side elements and smaller than the right side elements, and so on. If I have to find the first smallest element, where is it? If you look at it with your eyes, you know it is here.
SL.
First smallest element. Second smallest element is here. Third smallest element is here. Fourth smallest element is here. Fifth smallest element is here. What is the size of this container? 5. The sixth smallest element will not be in this container because it is greater than the size of the SL array. That is why this condition works. If the size of SL is greater than or equal to k, it means my kth smallest element is in SL. Now, what is the benefit of this? I can simply, okay, let me keep this example. I will write this down. Go down, go down, go down. The benefit of this is that I will know that my kth smallest element is in within SL. I can ignore SM and SR now. I'm discarding them. So if this is true, I can simply call my function in array SL. I don't have to go through the entire thing, SL, and find my kth smallest element. See, recursion. I'm using recursion here. Case 2. What if the size? What if SL is not greater than k? What if it's smaller? If it fails, case 1 fails. Case 1 fails means it means what if SL is lesser than k, and case 1 fails and something happens. What happens? Size of SL plus size of SM is greater than or equal to k. Now what will happen? It means my kth smallest element will lie somewhere here within SL and SM. But I said case 1 failed. Case 1 failed means my kth smallest element is not in SL. It means my kth smallest element will be in SM. That is the condition if case 1 fails and if the size of SL plus SM is greater than or equal to k. Case 1 failed and size of SL plus SM is greater than or equal to k. And if I am telling that my kth smallest element is in SM, I know that all the values in SM are equal to m because I only kept the values equal to m in SM. So that means I can simply say that my kth smallest element is m. This is the answer. M is the answer in case 2. I don't have to do anything else. Case 3, both
Else.
of the other cases fail. So basically, SL is less than K, and SL plus SM is less than K. I mean, basically, else. You can write if you write if you don't, if else. Uh, I mean, if you're using C, if else if and else. If you're using Python, if elif and else. So finally, what if both the above cases fail? Then you will know for sure that my kth smallest element is an SR. So I have to call the function on SR. But now the kth smallest element of A, is it the kth smallest element of SR? It is not. For example, just look at the previous example. 6. Okay, I want to look at the seventh smallest element of my original array, which is here. The seventh smallest element of A is not the seventh smallest element of SR. Seventh smallest element is the 7, 8, 9. Second smallest element. If you notice in 8, 7, 9, oh, first smallest element, right? It is the smallest element. First smallest element of SR. So when you're calling the function, you're supposed to put this number 1. Now, how do I get this number 1? You'll get this number 1, or in this case, it will be k minus size of SL minus size of SM. Now, how is this working? You can verify in the previous example k is 7, right? So 7 minus size of SL is 5, size of SM is 1. So 7 minus 5 minus 1 is 1. So that's how I got my 1, the first smallest element of SR. I am basically discarding all the elements of SL and SM. So I have to subtract the sizes of each of those arrays before I enter it in the function. So that's why I have k minus SL minus SM, the sizes. This is the algorithm. It works recursively. That's why I'm using the function f. That's why I defined f here. Where is f? Here, I defined the function f here. Now we are supposed to find out the time complexity of this function. Uh, the details I've mentioned it in the notes. I don't see. For example, if your randomly picked element, which is m, if m is the median, which is very rare, how likely is it that the randomly picked element is a median? Very rare, right? If it is a median, then there is a time complexity. What is the time complexity? You can see it says that if m is median, if m is median, what happens? You immediately, like, if case 1 is true, you will discard sm and sr. If case 1 fails and if case 2 is working, you don't have to do anything. Directly your answer is m. If case 1 fails, if case 2 fails, if case 3 is working, then you will discard sl and sm. So if your m is the median, it means you will either discard sl or you will either discard sr. Means approximately you're discarding half of the other elements. So your time complexity in that case will be uh, t of n by 2, because now you only have to search through half of the elements. The extra time that you take is consumed in traversing through the array, because we discussed this previously. You need O of n to make the containers. So O of n. If you look at this time complexity, you apply Master's theorem, you'll get T of n is this much in constant, not constant, polynomial O of n efficient algorithm. Previously we got n log n. Now we are able to do it in O of n. But then if you are paying attention, see, if m is median, how nice it is. M is median. It's not possible, no? So uh, you're supposed to specify. This is only true if M is median. If M is not median, then there are other things. Just go on to the next page of the notes. Just refer the notes. Everything I wrote it. I'm not going to discuss any of those because we have other things to discuss. Refer the notes for further discussion. Let me write it. Further discussion in the sense there is this discussion. What if M is lying in between? Just go through the notes. I'm not going through that. Refer the notes for further discussion. I'll not say it's not that important, but we have other important things. Did someone unmute themselves?
Dilip,
Yes.
is M is a median or kth smallest element? Why median came here in this question?
Median came here because we wanted to analyze the complexity of this function. If M is median, what is the complexity of the function? If M is not median, then you can't directly talk about the complexity of this function.
Okay.
In the worst case, I don't know. It's going to be. We will not get into the discussion. We'll just leave it as it is. The algorithm is important.
Okay.
I mean, even the analysis is important, but I don't think there is sufficient time for me to delve into the specifics of this specific algorithm. We have other things to discuss as well. Just refer the notes. I wrote whatever is necessary. Hopefully.
Okay, Dilip. Thank you.
You're welcome. Okay, fine. In the notes after this discussion, we have the proof for Master's theorem. You can just go through that. That is out of syllabus, anyways. I'm not going to discuss any of that. Uh, Closest pair problem. Closest pair problem will be the last main topic of divide and conquer. After that, we'll be moving on to greedy algorithms, which has two main subtopics, which is Huffman encoding and interval scheduling problem. So it's getting over fast. There's nothing much. Maybe I'll stay for a while and clear your doubts if you have any after I finish the entire thing. For yes, after I finish greedy algorithms. If you have any doubts in between, do let me know. I'll be happy to clarify them. Next problem, the eighth example under divide and conquer is the closest pair of problems. Points, sorry, closest pair of points. Yes, not problems. How nice. Closest pair of points, not problems. Closest pair of points. Points in the sense in R2, we're not discussing any other thing in R2. So we have our ordered pairs x comma y. You'll have all x comma y's, 1 comma 2, 2 comma 3, whatever. In our R2 space, we're supposed to find the closest pair of points. If you think about it, more than one pair can have the same distance. For example, if this is our R2 space, I have three. I have many pairs. I have NC2 pairs, but the closest of them are these three, right? These three are close. Any one of them can be the closest pairs. They're not emojis, they're pairs, and these are arrows. I mean, each of these pairs can have a distance of d in between them. So I can have multiple pairs having the same distance, and and there is no other distance smaller than this. So it's not that only one pair will have the shortest distance. I can have more than one pair having the same shortest distance. So why am I telling this? I'll come to this in a while. Input of this problem is what do you input? You input a set of points or an array of points. An array of points. You have some array of points. And remember, you can't sort an array of points because there is no ordering between x comma y. You can't say that 1 comma 2 is greater than 0 comma 0. That is false. This is incorrect, mathematically incorrect. There is no ordering between points in R2. You can say 2 is greater than 0, but you can't say 1 comma 2 is greater than 0 comma 0. If you remember complex numbers, you do know that, no? You can't compare two complex numbers. Same is the case with points in R2 space. You can't compare them. So there is no question of sorting. You can't simply sort two points and then just find the closest one of them. The output is the closest distance. I told you that more than one pair can have the closest distance, but the closest distance is just one number. So I can just say that the output is that one specific number. Additionally, you can give out the pairs also in the output. Which pairs have this distance, the closest distance. I mean, okay, let me just draw. I have random points. I have to find the closest. Okay, let me do it nicely because I have to use the diagram again, right? If I have points like this, uh, by looking at this set of points, you can see that this pair is the closest. I mean, this is the pair with the closest distance between them, the smallest distance. I should write the smallest distance or the least distance, not closest distance. The smallest distance. Now we have to design an algorithm which solves this problem. Uh, Fine. See, you can simply say that do divide and conquer. I will divide this into, let's say, there are some points. I will take one point. I will divide it into left half and right half. I will try recursively finding out the smallest distance here. Recursively in the sense, again you will divide this into half. Again you will divide this into half. And when you reach a very small sub-region, then you will start manually finding it. For example, uh, let's see the right side one. If I divide this into half, I'll take one point, I will divide this into half. At one point, what will happen is in some sub-region, I will have some countable number of points. Then I can start randomly, not randomly, I can do brute force there. I will look at this distance, I will look at this distance, I will look at this distance, then I will find out the smallest distance in them, and then I will come back from recursion. Instead of finding, see, brute force method is involving this one. You will compute all the NC2 distances. When you have n points, you will have NC2 ways of joining those points together. So you'll have NC2 distances, which is like, what is NC2? NC2 is n into n minus 1 by 2. If you're computing the distance, this is like order of n square. If you're using brute force, if you compute every distance and then find the smallest one in that, it will take like order of n square. Can we do better? Yes, we are trying to do better because we are using divide and conquer. So let's see. The algorithm says that you divide it into left half, right half, and then do it recursively. Keep dividing it into halves, half, 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 half. Finally, when you get like 2 or 3 points in your subregions, then you do brute force. Let's say if this is the case, then you can apply brute force. You can find the shortest distance, and then you come back. This is the basic idea. Now we'll look at the specifics. We'll look at the problems that this divide and conquer method has. Let's say the shortest distance here is here. The shortest. Let me call it DL. Left side, so DL. Let me call this DR. Let us say that I found this DL after doing recursion here. Left side I applied the function, I found out the shortest distance, the output was DL. Right side I found applied recursion, I found out the distance to be smallest distance to be DR. Now the thing is, how do I find out the smallest distance of this entire thing? I just have to compare DL and DR, whichever one is smaller. Let me call it D. I'll call D is the minimum of DL and DR. So I can simply say that my D is the least distance. But the problem here is, let's say I have a point here and here.
Hmm.
I have a point here and here. One is on the left side, the other is on the right side. When I apply recursion on the left side, the same DL will come because those are the closest points in the left side. DR will come here because those are the closest points on the right side. But these 2 points have not been accounted for because they did not lie in the same side. Just because they're on the different side. I told suppose there are 2 points here. Suppose there are 2 points. The worst case problem. If there are no such points, we are fine. Our problem is done. But let's suppose you have these 2 points here around this point, just along the boundary, and it's a distance. Let me call it. Let's say d dash. Let me call it d dash. Let's say d dash is less than d. But then our algorithm is not considering d dash because it's applying recursion on two different halves. It is not considering points where one point is from the left side and the other point is from the right side. It is not considering that. So now we have to upgrade our algorithm so that we consider these cases also. Now, how do I do that? The trick here is not the trick. The method is uh, you make every time you're comparing DL and DR, you make a strip. Uh, you make a strip around this point. The strip should be of the size. This is like this is D. This is also D. What is my D? My D is the minimum of DL and DR. The advantage, not advantage. Why are we doing this? The reason behind putting this strip is, I'll say this. There can be if there is any pair of points such that one point is from the left side and the other point is from the right side, if there is any such point, and if the distance between them is smaller than d, then they will lie within this strip. This is my claim. It is because, let's say, your point is here, and if there is any other point, let's say it's not on, one is here, the other is here. I am saying that this distance will if the distance between them is less than d, then they'll lie in the strip. Because if it is more than d, they will lie outside. No, because let me just zoom in. Is it possible? Ah, yes. One point is on the left side, the other point is on the right side. Ting, 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 ting. This is the distance between them. This distance is d. Uh, let's say this distance is d dash something. I'm saying that if these 2 points are lying within the strip, then d dash will be less than d. If d dash is more than d, it means this point will lie here. Only then will it be more than d, because you have this extra distance. This extra distance, if I call it, let's say epsilon, d plus epsilon is more than d, so then d dash will be more than epsilon. In the worst case, what will you have? This point is exactly equal to d, no? If it is lying on the line, then distance is d. D dash is the distance between this point and this point. So I'm trying to see the worst case. The worst case is the point is lying here on the yellow line, and the other point is lying exactly on the boundary of the strip. If the distance, if this is the case, if the distance between them is d, it's not less than d. If it is less than d, means it has to be inside the strip. Because see, by definition, the length of this strip is d and d, no? So if it is inside this, you'll get a distance that is less than d. You will get this case. This is not possible. It should, and if in case it is more than d, then you don't have to worry about it. But by for sure, if there is any distance less than d, they will lie within this strip, even if it's like this. I mean, I don't know how else should I say this. But you can be sure that you can think about it. Just keep drawing some points. You can use Desmos if you want. You can plot graphs there. Okay, but it's fine. I'll not get into the specifics. If you make this strip, for sure you will get all the points whose distance is less than d, such that one point is on the left side, the other point is on the right side. If both the points are lying on the same side, then my recursive function would have found out that those points are smaller, and that would have become dl and dr respectively. The only problem is if they are on the different sides. If each of the points are on different sides, then this strip will help us. Now, okay, I wrote this strip. Now, what do I do with this strip? From this strip, what I'm supposed to do is I will have some number of points. I don't know how many points I'll have. It depends on the input, but that will be of the order of n. It could be uh, half of the points could be here, or else 75% of the points could be here, or else just 5% of the points could be here. We don't know. But whatever be the percentage, it is some percentage of n, and constants are ignored. We don't consider the constant. So it is the number of points is in terms of n. Since the number, okay, fine. What is the other step? What do we do? Hmm. Now, what we'll do is apparently. Mhm. Okay, I will tell you what to do next. First, we will see how to do this in program. How do I get this strip and all? How will you be given points? The input will look like this: p1 of uh, x1 comma y1, p2 x2 y2, so on, pn xn yn. I told you you cannot sort the points, so it makes no sense to sort these points. But you can sort the points based on their x values or y values. You can do this. So the first step is sort these points based on their x values. Sort based sort points based. I'm just writing it in basic English, based on x values. So if you sort them, what will you get is you will get these values. You will get this one, this one, this one. This is the x-axis, no? You'll get these. You'll get this ordering of the points wherever they are. But the y values are not yet sorted. They're in random order, whatever be their y's. Because here, this y is more than this y is less than this y is less than this y, and so on. You still don't have an idea as to how the y is arranged. Okay, after you sort your points based on your x values, you will apply recursion on the left half and the right half. How do you do that? If your function is, let's say, I'll just say the function is f. It's simpler to write. Let's say the function is f. Should I use a different color? I'll use a different color. Second step is you apply it recursively. No? How do you apply? How do you know the left half and right half? Left half is basically uh, uh, the points with. Okay, let me write the sorted order as well. Let's say you obtain P, or let me change it. Uh, P, what do I take? Q? Okay, I'll take Q. After I sorted, I got some order. No, I should. What do I take? Mm, okay, I'll take P dash. This is the sorted order. So P1 and P1 dash need not be the same thing. This is the sorted order. The second step is to recursively apply my function f. So f is applied on uh, the points p1 dash, p2 dash. Since they're sorted, I will go on until xn by 2 dash. So this will go on till this is dash. This will go on till since I have n points, so n by 2 dash. My left half is basically this. All my points of the left half are this collection p1 dash, p2 dash, pn by 2 dash. Why is that? Because they are sorted based on their x values. All the points here are having less x values, all the points here are having more x values. Recursively, I should also apply the same function f on the right half. Right half, but you're supposed to include the midpoint as well. I'll tell you why. So you include this also, this point as well. What is this? And so on till p and dash. You are recursively applying the function left half and right half. What will happen is here you will get your dl because the function is f is the function, our algorithm. I'm calling the algorithm using the function f. We didn't yet define f, but I'm calling it recursively. Even if you remember in merge sort, while writing the merge sort, you will write merge sort within the definition. That is what I'm doing here. If you remember, like merge sort the left half, merge sort the right half, then merge the entire thing. This is the same thing I'm doing here. You apply the function on the left half, you apply the function on the right half, you'll get some values. The first answer will be DL, the next answer will be DR. I asked you to include the midpoint as well because this point is there, no? Even its distance will be compared with other points. So, for example, if there is any other point, let's say here, this will give me D. If there is any other point here, this will give me D. That could have been the closest pair of points as well. Because if I ignore the midpoint, let's say, if I only include the midpoint in the left half and if I ignore it on the right half, then this distance will not be considered if I don't include the midpoint for the right half as well. Then we would be potentially missing the smallest distance. That's why the midpoint must be included in the left half as well as the right half. It's in both halves, whichever point is along the midpoint. Midpoint in the sense the median, the middlemost x value, the median, not average, but the median. Why median? Because median is the middlemost value based on their x values. So that's why I'm including the median on both the halves. If I do this recursively, I'll get dl and dr. Now the problem is with the strip. We'll come to the strip later. And then since you're using recursion, you have to look at the base cases as well. Base case is basically if you have just 2 or 3 points, you can use brute force then. Okay, how do I find the range? The range, I mean the strip. The strip is basically the points located in this range. So let's say if if x belongs to this one, what is the range? Uh, x n by 2. This is the median value, right? Minus. Okay, I didn't define d. No, d shall be defined as the minimum of dl and dr. Minimum of dl and dr. The third step is you make a strip, right? How do you know if it is a strip? If x belongs to this range, xn by 2 minus d and xn by 2 plus d. If you notice that that is the range of x within the strip, right? So if any of your points have x lying in this, then p of xy is in the strip. So you can, while programming, you can make an array of points. You can make an array of points which will include all the points within this strip. So if there are any points here like this, all of them will get into the strip. Okay, I did not tell you what are we supposed to do after we get the strip, right? So after we get the strip, what you're supposed to do is now you sort all the.
Cell minus D అంటే అవుతుంది. ఇంకో లాస్ట్ పాయింట్
So the next point is that once you get your strip, you're supposed to sort all the points in your strip based on their y values. So sort, which color am I writing with? Okay. It's supposed to be green. Anyways, fine, it's fine. Sort points. I mean, these steps are there in the notes, but they're slightly specific. Sort points in. I'm writing it very basic, very in basic words. Sort points in strip with respect to y values. So y values. Once you do that, you will get an idea as to these values. You will get to know this value. You'll get to know this value. You'll get to know this. You'll get to know this, and so on. You'll get to know the y values as well. So if you sort based on their y values, let's say in an ascending order, your strip will look like this from top to bottom. You'll be starting from here, irrespective of their x values now, because now you sorted them on their with respect to their y values. Their x values will get jumbled. So you will start from the bottom. So you will start here, then you will go here, then you will go here, then you will go here, and so on. Because your array doesn't store this graph, right? It will take a lot of space. We are just looking at their x and y values. Now what you're supposed to do is, after you sort your strip, after you sort your points in the strip based on their y values, the next step is you're supposed to now you can use brute force, but you don't have to compare all the points in the strip with one another. You just have to start from the smallest point and compare its distance with the next 7 points. Why 7 points? Because there is a proof that will that states that you just have to do only 7 comparisons. That is given. Okay, I'll just show it to you here. Let's say this is the strip. This is the strip. This is distance d. This is distance d. And let me just make more divisions. This is the midline, the line passing through the median. This is distance d. This is distance c. Let's say your point. Let's say your point is here. It's still in the strip. Uh, how many other points? Like how many other points are possible such that the distances between those points and this point is d? If the point is here, then other point could be here. Then the distance between them is d. It could be here as well. Or else, let me just put all the points. Let's say a point is here. It need not be on the corners. If there is any other point within the same box, its distance will be how much? Okay, let me start once again. What is happening? I have this strip. Let's say your starting point in the strip is here with the least y value. We sorted the strip based on the y values, right? Now my question is, can there be any other point within this small box? The answer is no, because the distance between these 2 points will be less than d. Because if you look at this square, this is d, this is d. This, if you take the distance between any 2 points here, they will be less than d. Any 2 points between the square. If you look at the diagonal, the distance between the two corner points is d root 2. Is it d root 2? D root 2 है ना? How much is the distance? D root 2 is Hmm. D root 2.
Yeah.
D root 2 is more than D, so that is not a problem. See, if a point is here, if a point is here, its distance is D. If a point is here, if a point is here, its distance is less than D. I am telling that such a point is not possible because I told you that when I applied recursion on the left side of the points, I obtained dl, and d is defined to be the minimum of dl and dr. So by definition, if there is any two points whose size is less than d, it's like it's a contradiction. I told you that the smallest distance in the left side, in the left half, is dl, and the minimum of dl and dr is d, and d should be less than or equal to dl. No two points on the left side will have distances less than d, and I'm telling that here the distance between two points is less than d, which is not possible, because if it is less than d, it means it is less than dl as well. That is not possible. You can't have a distance that is less than dl. That's contradictory. That means the least distance between two points in the same box is supposed to be d. You can't be going less than d. That means if you have a point in this box, the next closest point should be outside the box. It can't be within the box, because the moment it is within the box, the distance will become less than d, which is not possible because d is less than or equal to dl. dl is defined by definition. It is the least distance between two points belonging to the left half. So if you have a point here, it is supposed to be outside the box, the next closest point. So this is not possible. So in the worst case, in the same box, you can have four different points. That is possible if you have all those points in the corner. In the worst possible case. In a general case, if your point is here, all the other points will be outside the box. They won't be anywhere near the box. So I will look at the worst possible case. Point in the corner, point in the corner, point in the corner, point in the corner. So at max, in this small region, you will have four points. On the right side, it's the same thing. Point in the corner, point in the corner, point in the corner, point in the corner. These two are the same points. They're lying in the same place. But then I am considering them to be different because one, I told you, right? Whenever there is a point lying on the line passing through the median, you're supposed to consider that point to belong to both the left side and the right side. So uh, I hope that made sense. So if there is, in the worst case, let us look at the comparisons, like how many distances am I supposed to look at. If this was your point, if this were your point, 1, 2, 3, 4, 5, 6, 7. You're supposed to make 7 comparisons in the worst possible case, and then your job is done. You don't have to look at any other points in any other boxes, because you know that the distance will be more than d in that case. That's why you're supposed to make only 7 comparisons. You can think about it in your free time. I mean, okay, fine. Even if this doesn't sit in your head, the thing is, when you sort your points in the strip with respect to the y values, let's say it's in increasing order, you're supposed to compare this point with the next 7 points: 1, 2, 3, 4, 5, 6, 7, and so on. You start with the next point, you compare it with the next 7 points. So, 7 comparisons. And then you go on. So, let me write 7 comparisons. Uh, every point in sorted strip, or every point in strip is compared with the next 7 points, because there is proof, there is a proof of sufficiency. You just have to compare with the next 7 points. Within this, you're supposed to find if there is any distance smaller than d. You will get the distance. You will not get any distance smaller than the outside the strip. So after you finish comparing each point in the strip with its next 7 points, finally you will get some value. After you finally get some value, let's say it's d dash, then you can compare it with the d. If d dash is smaller, then d dash is the smallest point. If d is smaller, then d is the smallest point. So our final answer is basically, final answer is minimum of d dash and d. D dash is the distance obtained while checking for the points within the strip. Each point is compared with the next 7 points. How next 7 points? Because we sorted them based on their y values. So this is the algorithm. Now we are supposed to find out the time complexity of this algorithm. So we'll start with step 1, sorting points based on x values. The best we can do is we can do this in order of n log n. The best sorting algorithm takes order of n log n. You're recursively applying the function, right? So if I define the function to take t of n time units, so if I define this is t of n, if this is t of n, then my recursion will take t of n by 2. This recursion will also take t of n by 2 because I'm decreasing the size by half. This is just this is order of 1, so that is not much of a problem. Now making the strip, I have to traverse through the entire array of points and store those points satisfying this condition. X should lie within this. So x is greater than this and x is smaller than this. Only then will that specific point will lie in the strip. Since you're traversing through the array of points, and since the array of size of the array is n, this traversal will take order of n time, sorting the points in the strip with respect to y values. I told you that the number of points in the strip is some percentage of n. We do not, so some percentage of n is something, some k percentage of n, some k by 100 of n, whatever, some number, some k of n, k times n. This k is smaller, less than 1. So you have these many elements, but it is still see, I'll just if you sort kn elements, it will take kn log of kn. If you simplify this, what will you get? Kn log n plus log k, right? This is nothing but still O of n log n. We will ignore the constants. You will ignore the coefficients, you will ignore the constants. So this will become, how do I ignore the coefficients and constants? Kn log n plus kn log k. This is a coefficient, k log kn. Here k is a coefficient. You can ignore this. N log n and n, which is greater? N log n is greater. So I can simply say this sorting will also take O of n log n. It is not that all the n points are within the strip. Some percentage of the points are within the strip, but you will still write it as O of n log n because we've just seen what is happening. The constants and coefficients are ignored. Now comparison. For every point it is just O of 1 per point, because you are simply making 7 comparisons, which is constant. O of 1 represents constant time units. So per point, you're expending only O of 1 time complexity. But then we have approximately some percentage of n, so some kn points you have within the strip. So constant time units per point, you have kn points. So total time complexity is O of kn, which is basically order of n total. 1 point is order of 1. You have around n points, some percentage of n by 2 or n by 4 or whatever, n something. Total order is O of n because you will ignore the coefficients, you will ignore the constants. So do we have? Hmm, let me just verify if my analysis is right. Okay. Uh, when I said you're sorting points in the strip with respect to y, I'll just let you know what is happening. You have n, you're dividing it into n by 2 and n by 2, and then recursively applying it within the halves, right? So n by 4, n by 4, and so on. So in a general case, it is something like n by 2 power I, right? I is anything from 0 to whatever. So in a certain half, if I'm sorting my elements in the y strip, it will take O of input log input. Here input is n by 2 log n by 2. I can ignore the coefficients. Log n by 2 is you can't ignore this by 2 here because log n by 2, can you ignore it? Log n minus log 2. No, I think you can ignore it. Still n log n. Okay, fine. It's still n log n, so it's not a problem. Anyway, I thought it was a problem. Fine. Okay, time analysis. So we will add all of this. We are doing recursion twice, 2 times t of n by 2. Anything else? O of n is there, O of 1 is there, O of n log n is there. O of n log n will overtake O of n, so I don't have to write O of n. So this will be O of n log n. I can't apply my master theorem here because this is not a polynomial. So now you're supposed to use your logic. How do you use your logic? So when I have n points, I'm dividing it into n by 2 and n by 2. The time taken to solve this is t of n by 2. The time taken to solve this is t of n by 2. The time taken to sort this is n log n. The time taken to sort this is n by 2 log n by 2. But then I have two of those. So I'll just write 2 of n by 2 log n by 2. I have two of them. I'm performing two of them. If I have n by 4, n by 4, I will have four of them. 4 of n by 4 log n by 4. This will go on until I get 1 or 0, whatever it is. This will keep going on. So if I do summation, n log n plus n log n by 2, so on till n log n by n is 1, so log 1 is 0. This becomes 0. This is nothing but n log n by 2, n by 4, n by 8, it goes on, n by 16. I can assume that n is some 2 power k, then this goes on till this one. This is nothing but n log n power, what is this? 1, 2, 3. What does this become? Okay, let me just write n by 1, n by 2, n by 2 square, n by 2 cube, n by 2 power k. 2 power k is nothing but n. I have k. Okay, fine, I got it. So n log n power k. How many n's do I have? K plus 1. This is nothing but 2 power something. This is going out of hand. Hey, calculation. I mean, okay, fine. Do the calculation at home or wherever you're at hostel. This will approximately be n log n square, approximately. Just do the calculation at home. Do whatever you want. You just have to add all of this. You will get n log n square. I am not doing that here. It is doable. You just count. I'm running short of time. So, okay, why did I do all of this? Now I can simply rewrite my recursive relation. I don't have to rewrite. It's directly the answer. This is your answer. No master theorem, nothing, because it was not in the standard form. I mean, see, I wrote this because if you have input n, it takes this much time to sort your y strip. Then you are subdividing it into left half and right half. Each half takes n by 2 log n by 2. You have two such halves, multiply with 2. Four such halves, multiply with 4, and so on. So add all of those numbers, you'll get something that is approximately n times log n whole square. So your time complexity is this much. This is the time complexity of the closest pair of points. You can bring it down to O of n log n, which I discussed in the notes. You can bring it down to n log n if uh, x and y arrays are sorted. I mean, P is sorted with respect to x and y, and it has to be given as an input. Instead of simply sorting based on x, you sort based on x as well as y. Then there is a possibility of decreasing the time complexity. The reason as to how this is happening, I mentioned it in the notes. You can just go through it. Because after I sort with respect to x and y, I don't have to sort my strip with respect to y once again. I can just traverse through this sorted y sorted sort with respect to sort if p sorted, if points are sorted with respect to x as well as y, and these arrays are given as input, then you'll be able to do it. I mentioned it in the notes. You can look at it. Basically, then my recursive relation just becomes t of n 2 times t of n by 2. Then my sorting will not take time because I already sorted them beforehand. Then it will be this one. You just have to go through how is this happening before. If you apply Master's theorem, then you will get this one. I mean, you have to think about it. Just think. I'm not telling. Think. Or you could Google it. How do I decrease the time complexity from n times log n square to n log n? There are discussion. There are forum posts. You could go through it. Next, okay, this is the end of divide and conquer. Greedy algorithms. There are just three things. Kruskal's and trims is nothing that we'll get over in 5 minutes. After that, we have Huffman encoding and interval scheduling problem. Uh, the proofs of the statements which I will be using to explain the Huffman encoding or interval scheduling problem. I will not be going through that. It's in the notes. You can just go through them. I'll just give the basic idea. But I will be telling you what the Huffman encoding is, and I'll tell you what the interval scheduling problem is about. So if this is done, I will simply end this and write greedy algos. Algos. Fine. Greedy algos, we saw it in the last semester. We saw it when we were trying to make minimum spanning trees given a connected graph. We used primps and Kruskal's. So if your input is a connected undirected graph with edge weight, so if you have, I'll just write this example one. You have graphs. You have a graph. It is connected, so you can't have any node that is not connected. You have a graph, and you have some edge weights, random edge weights. You're supposed to form a minimum spanning tree. What is a minimum spanning tree? First of all, it should be a tree. How is it a tree? It should have exactly. It is it is acyclic, and then it has exactly n minus one edges, where n is the number of vertices. How does it become minimum spanning tree? If the sum of all the weights of the edges in that particular tree is the least possible value. If it gets the least possible value. So okay, I'll give an example. Let's just take a small example. I have some. I mean A, B, C, D. So 1, 2, 3, 4, 5. A, B, C, D. The minimum spanning tree of this is, if you look at it, I have to cover all the nodes. I should not miss any nodes, and the sum of all the edge weights should be the least. So that is possible. Simply just write A, B, C, D. 1, 2, 3. I covered all my nodes. This is a tree because it has exactly 4 minus 1 edges, and the sum of all the edge weights is it has the least possible value. If you make any other tree, it will have a bigger sum of edge weights. So this is my MST. Now the question is how to get this MST. You have two algorithms. One is Prim's, the other is Kruskal's. Prim's is basically you. Okay, I'll tell first Kruskal's. Or okay, fine. I wrote Prim's here. Prim's is basically you select a vertex, some random vertex. Let's say I will select. I'll select D. After I select D, okay, let me put this graph here. Copy. How do I paste? I will apply these two algorithms. So Prim's, what does Prim say? It says that first take one random, so whatever, I don't just take a random. Oh, sorry, take some vertex. I'm taking D. From here, you're supposed to select the shortest edge connected to it. So to D, what are the possible edges? 4, 5, 3. The shortest one is 3. So you do that. You add it to your tree. Then find the next shortest edge from D and C, within D and C. So D and C you've selected. From here, you're supposed to find the shortest one. So you have 4, you have 5, you have 2. So from the selected vertices, the shortest edge is 2. So I'll add that also, 2. Now your selected set increases. Now your selected set is D, B, and C. D, B, and C. Now you're supposed to select the shortest edge. I mean, see, uh, yes, A is only remaining. So B, D, fine. B to A. B to A is the shortest because 1 and 4. 1 and 4 means 1 is shortest. So I will have A. So the Prim's algorithm is basically select a random vertex. After you select a random vertex, choose the edge with the with the least edge weight connected to the vertex you selected, and then you add that vertex also, whatever is connected. Now, after you get two vertices, from these two vertices, find the next shortest edge, add it to your selected tree, and keep continuing the process until you get a tree. There is a problem in between. If there is a cycle, you have to ignore the edge. Ignore the edge if it leads to the formation of a cycle. Kruskal's. Kruskal's, it starts the opposite way. You don't select a vertex, you select an edge. Select the shortest edge possible, which is basically the edge between A and B. So add AB. Or let me change the tree a bit, the graph a bit, so it becomes nice. 1, 2, 5. If you apply prims here, let's say you selected B randomly, B to A because that is the shortest. Then 4 from A to B, I have 4, 5, 3. 3 is the shortest, so B to C. Now my selected vertices are A, B, C, no? A, B, C. From A, B, C, I have 4, 5, 2. Closest is 2, so I will add 2 here. This is my MST. Now I will use Kruskal's. Kruskal's is telling that choose the shortest edge. Shortest edge is AB. A, B. Done. Then it says choose the next shortest edge. The next shortest edge is C, D. It is not a tree yet, it is disconnected. A disconnected graph can never be a tree because a tree by definition is connected. But don't worry, the Kruskal's algorithm will output a tree at the very end. The next shortest edge is 3. So you add that edge. The next shortest edge is 4. Uh, but 4 will cause a cycle. Oh, I mean, I don't have to consider much now. I already got my tree here, so it's fine. I have exactly 4 minus 1 edges. I don't have to look for more edges because in a tree I have exactly n minus 1 edges. Kruskal's is done. In case your shortest edge is causing a cycle, you ignore that edge and move on to the next edge. That is the algorithm. So whichever algorithm you are using, you'll get the same MST. So left side and right side, you got the same MST. This is Prim's and Kruskal's. It is under greedy algorithms because it is being very greedy. Prim's is telling that choose the shortest one, choose the shortest one. I mean, shortest edge that is connected to you. Choose the shortest edge connected to you. Kruskal's is telling that out of the entire edge set, find the least weight, find the least weight, find the least weight. Keep adding it.
అంటే ఫస్ట్ తర్వాత ఇది వస్తుందా?
AB in Kruskal's first AB came, then DC came, then BC
DC.
came. Finally, you'll get a connected. I mean, you'll get a tree. Tree is connected. So this is a mistake. This is part one. Our first example, which uses greedy. Prims and Kruskals are both greedy algorithms.
So
We did not discuss the complexity. We did not do the complexity analysis of this, so I'll not be discussing it either. I don't know if they will ask it or not. Yes, in the notes you can see there is a proof as to why does the best sorting algorithm take O of n log n. You can just go through it. I will not explain it. It's self-explanatory. You can just go through it in the notes. So the next, yes, next is Huffman encoding. The second example, Huffman encoding. Huffman encoding. After Huffman encoding, it's interval scheduling. Interval scheduling is small. Huffman encoding will take a bit time, maybe like 10 minutes, then we'll see. Before that, you're supposed to know some things, if some notations. If S is a set of some characters, then S star will be considered to be the set of all possible strings based on the. Okay, let me write it. Set of characters. If S is a set of characters, then S star shall be considered to be the set of all possible strings on S. So based on the characters of S, you make any string of any length, collect all of them and put it together. You call it S star. That is the notation we'll be using in Huffman encoding. One more thing you need to know about the numbers here. If there is a binary string, let me put this here. If there is a binary string of length k, so you have k digits of you have k binary digits representing one string. How many possible such strings are okay? How many such strings are possible? Because okay, we need a number now. The number is, see, the first bit can take two values, 1 or 0. The second bit can take two values, 1 or 0. So 2 into 2 into 2 k times. The possible number of binary strings of length k is essentially 2 par k.
percent normal set.
S is a set of characters. So if I have a binary string of length k, I will get 2 power k such strings. Different strings, unique strings. Length is k. Number of strings is 2 par k. Now I'll do the exact opposite. If I say that I have n strings, if I have n strings, what will be the length of each string? Just do the opposite. You assign 2 par k as n. This means k is log n base 2. So this means that the length of each string is log. Uh, this is basically string length. I just did the opposite. From the previous discussion only, from here, I just did the opposite. If I have n strings, or if I have, they're unique strings by the way, so if I have n unique strings, or I can simply say, for the sake of Huffman encoding, n unique strings, or I can assign each string, I can associate each string to a symbol. This will be helpful in our discussion, which we'll be doing in a few minutes. So if you have n unique symbols, each symbol will have a binary representation of length log n base 2. Since binary bits can't be of, like, I can't use 1.5 bits and so on, I'll take ceil of log n base 2. So I will call this seal of log n base 2 is the length of binary encoding. So is the length of binary encoding. Basically, I'm representing each symbol or string using binary, and its length will be at least, not at least, exactly seal of log n base 2. Length of binary encoding of each symbol. Having keeping all these things in mind, now we'll proceed to Huffman encoding. Uh, I'll just wait for 10 seconds. I forgot to give 10 seconds break every time. Fine, we'll wait for 10 seconds. I think that should supposedly be 10 seconds. Huffman encoding. Okay, we'll see why. We'll look at Huffman encoding in a while. First, we'll look at encoding in general. Let's say my S or okay, fine. We'll use a diff. Fine, we'll go on with this. If S is just A, B, C, D, what do you think my S star will contain? My S star will contain anything. It can contain like AB, AC, AD. It can contain. It's an infinitely large set. You have all possibilities. You can do anything. Ba, whatever. CAD. It has all these possible strings. So if you want to make any message using these four characters, all those messages will be a part of this S star. You can't make any message that does not belong to S star using S. So any message that is based on S will be a subset of S star. I mean, not subset, it will belong to S star. Now let me try encoding my ABCDs into binary. Here I have four symbols. How much is the length of each symbol in binary? The length will be seal of log n base 2. We discussed if I have n unique symbols, the length of each binary encoding will be log n base 2. I have four symbols, so log 4 base 2 seal is basically 2. So this formula is telling me that I will require 2 bits to represent each symbol. Is it true? Because if you, let's say, I have A, I will use it as 0, 0. B is 0, 1. C is 1, 0. D is 1, 1. I am able to represent ABCD using just 2 digits, 2 bits. If you use less number of bits, you will not be able to represent. If you can just see, if I use A as 0, B as 1, if I use C as 0, whatever, 0, 0, or D as 0, 1, the problem is now C can be either interpreted as C or it could be interpreted as AA. This is causing confusion. This will cause confusion. To prevent confusion, you have to ensure that the size of each symbol in binary is this much, seal of log n base 2. We just looked at how to get this number. So now I can easily encode anything. So for example, if you're trying to encode, if your message is bad, you're sending a bad message to someone, its encoding will be in binary, encoding of M, message is bad, so your encoding of M will be, if you're using the correct encoding, so it will be 0, 1, 0, 0, 1, 1. If you're using this encoding, bad will be basically 1, 0, 0, 1. But then this can have different meanings. This could also be B, C, B. It could be B, A, D. Okay, that is bad. I mean, there is still ambiguity, right? But there is no ambiguity here. It is confirmed. From here, if you see, 0 1 is B, 0 0 is A, 1 1 is D. There is no ambiguity here. But there is ambiguity here. There is ambiguity because you're
One one
using,
DLI in this one.
because I defined 1 1 D. I defined it to be here, using encoding here. I'm using this one here. There is ambiguity here. There is ambiguity because you're using, this is because you're using less number of bits. So the problem is, if you try to decrease the number of bits that you're using to represent a symbol, you will get a problem. You might land into some problem like this. You'll get ambiguities. But now the question is, some person is asking, I want to reduce this size. This is taking 6 bits. Can I send the same message uh, in 5 bits or 4 bits? Is that possible? But if you've been paying attention, you would tell that if you reduce the number of bits, you might get ambiguity. So here is where Huffman comes in. He does something. He has an algorithm. It removes any kind of ambiguity, and simultaneously is decreasing the number of bits as well. So what is the magic is doing? We'll look into it. Uh, Before that, we'll just do some calculations associated with this one. So let's say S has some symbols, S1, S2, and so on till SK. So the alphabet is a collection of letters. So there are K unique symbols in this. S star means, S star is any message. S star is a collection of all possible messages or strings. And let's say my message is something like M1, M2, MN. Some message is there. M1 is something from any MI belongs to S, because my message is based on the letters of S. And let us say that SI appears, or let's say SI, okay, SI appears, let's say uh, some number of times. Okay, let me write in terms of fractions. If SI appears, give me a number, give me some variable. A, yeah. Did we use A before? Okay, I'll write it like this. SI appears these many number of times. Frequency of SI is basically the number of times it appears. And I'm associating a fraction, Fi. I'm defining it to be frequency of Si divided by n. N is the size of the message. My message has n letters, so this is there like this. Or you could also, if you look at, I don't know, reference books or something. I did not look at them. I just saw it in a post. This is basically the probability of uh, or probability of the occurrence of Si. Out of n letters, Si appears so many number of times. So that divided by n will give you the probability. So this fraction is basically Fi. So Fi will tell you the probability of Si. How many times does it appear by the total number of letters in M. And you know that the summation of the total probability will always be 1. So I goes from 1 to, how many letters are there? N. N letters in the message M. Now the thing is, I told you the size of each symbol in the alphabet must be of size log something base 2. This something should be the size of the message. Message or size of the alphabet. The size of my alphabet is K. K is the size of my alphabet. So here k will come. In order to avoid ambiguity, I should have at least these many bits representing each symbol. Now let us see how many bits does my message take. So if I have to find the size of my message, size of m, so I should simply find the size of m1, size of m2, and so on. Or size of actually encoding of m. How much size does this take? So I should find the size of encoding of m1. I mean, I'll just write it in terms of summation. It makes life easier. Length of encoding of mi, where I is from 1 to I is going from 1 to n. But then I know that mi, uh, this is also nothing but I can simply write it like this: length of encoding of si, and I know that si appears how many times? Frequency many times. No, this I can simply write frequency times of si. Now here my I is going from 1 to k, because see, if I have a letter A, B, C, D, 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 the size of my encoding will be size of this plus size of this plus size of this plus this plus this plus this. Instead of that, what I'm doing is I'm writing A is appearing one time, B is appearing one time, C is appearing one time, D is appearing three times, multiplied by the sizes of each of their encodings. That is what I'm doing. That's why this changed to this. You can think about it. It's the same thing. The value is the same. There is no mathematical conversion. It's you think about it and then you reach to this step. Now we just saw that the size of each symbol, or the size of each encoding is, let's say, the size of each encoding, it should take this much space. It's a constant. Each symbol has this much size. So I can simply write, and frequency of Si is nothing but n into Fi. Fi is the probability, n is the size of the message.
Sigma into F by 1 అయిపోద్ది.
No, no, I will see. N F. Oh yes, and length of each encoding is basically seal of this one. N is a constant. My this is a constant. Both of them will go out. What remains is summation of Fi, which is 1. So this is the final answer. So the size of my message is this much. See, you don't have to do all of this calculation. You have n symbols in your message. Each symbol has this much size. N into that size will give you the total length of the message. But the reason why we did all of this is we are trying to know if there is a way of reducing the number of bits while encoding. Can I send the same message with less number of bits instead of this much? If you look at it, if you look at the this box, this is the main thing. Here n is constant, you cannot change the size of your message. Fi is constant, you can't change the probability. You can't change the number of times a symbol appears in the message. But look at this. You could probably change this. How could you change this? You could change this if this is a variable number. But not this box. Let me put this box. If the length of each symbol, if the length of the encoding of each symbol is different, if they're not the same, then there is a possibility of either increasing the entire sum or decreasing the entire sum. We want it to decrease. So Huffman proposed a solution. What he and we did notice, right? If we give different, what is it? here we gave different lengths, right? Here length of A is 1, the encoding. Length of B is 1. Length of C is 2. Length of D is 2. If you give such encodings, you'll get ambiguity. So how does Huffman prevent it? We'll look at it. He reduces the length of each symbol. At some places, he has to increase it because if you reduce the length of each symbol, you will run out of encodings. You can't represent A, B, C, D with just 2 bits. It's not possible. If A is 1 and B is if A is 0 and B is 1, you ran out of symbols now. You can't represent C and D. So you will need sufficient number of symbols. So we'll look at how Huffman did it. Mm, Yes, so now I'll be telling some statements. I will not prove them, but I will be using those statements to continue with Huffman's encoding. The statements are this one. The first statement is every. The proof is in the notes, by the way. You can go through it. Every binary tree corresponds to a prefix free encoding. We'll look at the example. We'll look at an example. What do I mean by prefix free encoding? Prefix free encoding is something that does not look like this. This is not prefix free because here A is 0, but C is 0, 0. A is a prefix of C. Prefix in the sense something that appears in the front. So you'll get this ambiguity. A is a prefix of C. A is also a prefix of D. So that is the problem. Uh, the encoding of one symbol should not be a prefix of the encoding of any other symbol within the same alphabet. If you not allow that from happening, then you will be happy. Why happy? Because there'll be no conflicts. For example, if you, uh, for example, okay, let us look at an example. Or I'll draw a binary tree and then we'll look at an example. Let's say the message I want to encode is A, B, B, C, D, 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 whatever. Now I'm saying that every binary tree corresponds to a prefix encoding, right? And what kind of binary tree? The number of leaves should be equal to the number of symbols. Number of leaves in the tree should be equal to the number of symbols. My symbols are in the size are in the set S, no? So I'll simply write this. I'm not going to write. You know, S is the set of all symbols you have. Number of leaves in the tree should be this one. So let me draw some random binary tree. How many symbols do I have here? I have A, B, C, D. So I will draw some random binary tree with 4 leaves. I'll just draw it randomly. It should be binary tree. It should be binary tree means it has see it can have at max 2 children, right? It can have either 0 children or 1 children. Finally, I need two. Wait, I need 4 leaves, no? So one, two, three, four. Okay, let's say I drew a random binary tree. I'm saying that this leads to a prefix free encoding. Now, let's see. I will define my left to be 0 and right to be 1. So 0, 1, 0, 1, 0, 1, 0. This is a binary tree. I'm telling this is prefix free. Let me assign values. Uh, Let me randomly assign values and then we'll see. This is A. I'm randomly assigning for the moment. Do I
8 ఉన్నాయి కదా అక్కడ 7 ఉన్నాయి.
leaves? I need 1, 2, 3, 4. I need 4 leaves.
ఇక్కడ 7 ఉన్నాయి, ఇక్కడ కూడా 7.
Size of S, not M.
ఓకే.
S is this one. This is your S. This is your M. The number of leaves in the binary tree should be the size of your alphabet set. Your alphabet has 4 different letters. So I'm randomly assigning, but you're not supposed to randomly assign. But we'll look at it. We just want to prevent prefix free encoding. We'll see how that is happening.
దీనికి ఇటే ఎందుకు వచ్చింది, ఇటే
I made a random binary
Okay.
tree. I'm telling every binary tree leads to a prefix tree
Okay, okay.
encoding. I took a random binary tree such that it has 4 leaves. So according to this binary tree, I can make any other binary tree. You can make one as well. Not one, you can make many. So according to this tree, my A is 0, my B is 1 0 1 0 1 0 1 0. My C is
0
1 1 1 0 1 1 1 0 1 0. Oh wait, C is 1 0 1 1 0. D is 1 0 1 1 1.
A 10111.
See, A is, to reach A, you will go like this. To reach B, you will go like this.
Okay.
To reach C, you will go like this, this. Yes. To reach D, you will go like this.
And you add just 10111.
Yes. And now, if you encode it, see, I'm not encoding. You can encode it. But the problem here is, if you encode it using this way, the size of the message is increasing, right? C is taking like 5, A is taking 1, B is taking 4, 4, D is taking 5, 5, 5. What is the total size? 28, 29. But if I use the fixed encoding scheme, I will simply get it in uh, length of the message is 7, log size of the alphabet is this one. So this is 14. If I would have used a fixed encoding scheme, I could have just represented the same message in 14 ways. Now, where is the efficiency? Here we are not talking about efficiency. Here we are trying to look at prefix free codes. Let us look at the encoding. Is A a prefix of B, C, or D? No, because no other encoding is starting with 0. Let us look at B. Is there any other encoding starting with 1010? No, there is no 1010 in any of the others. The same is the case with C. There is no. Is there a mistake that I did? Okay, there is no other encoding beginning with 10110. There is no other encoding with 10110. So when you are decoding your message, you will not find any ambiguity. That is the benefit of having prefix free encodings. You will not get any ambiguity. So let me reduce the size of the message, then we'll look at an encoding. Let us say it is cab. I need to use D also. Cab. So the encoding with this thing will be C, 10110 uh, 1010 1011. This is not efficient, but we are looking at prefix free things. So let's see, 101
ಇದರ
1
వచ్చినందుకే ఇవన్నీ యాడ్ చేసావా?
CABD. CABD.
C is 10110.
10
A is a 0. B is 1010. D is 103.
So how do we decode this? If I see 10110, that means it is C. Then we'll move on to the next one. 0 means there is only one letter A. Next 1010 down, done. I found a letter B. 10111. I found a letter D. So there is no ambiguity. There is no possibility of an ambiguity when you're using a prefix free encoding scheme. How do you get a prefix free encoding scheme? Use a binary tree. What is the proof behind this statement? See, just look at the notes. It's simple. I mean, it's simple. I mean, I could tell it.
ఇది ఇంప్లిమెంట్ ఇన్ హాఫ్ మ్యాన్ అనుకోవాలి.
Implementation is అది proof కాదు, అది code అది.
నేర్చుకోవాలా ఎగ్జామ్
Analysis చేయాలి, time complexity అది. ఓ లేట్ అయిందా రికార్డింగ్ ఉంటుంది. ఇది ఎంత టైం పడుతుంది? Fine, the proof is simple. See, if you have any encoding scheme, let's say it is 101. Let us say that is the encoding scheme of some character S1, let's say, or let me make a new tree. This is a binary tree, 0 1 0 1, S1, S2, S3. 0, S2, S3, this is 4. Let's say there is 1, 0, 1, 0. Let's say 1, 0 is some, let's say the encoding of some SI is a prefix of some encoding of SJ. This means that encoding of SJ is basically encoding of SI with some zeros and ones on its right side. This is what it means when we say encoding of SI is a prefix of encoding of SJ. Now, what happens here is I said that the encodings are the leaves of the binary nodes. So, if this entire thing, some random thing, some symbol SI, its encoding is a prefix of encoding of SJ. So encoding of SJ can be represented as encoding of SI followed by at least one string, binary string, or it can be anything 1001 or just 1 and 0, but at least one binary string. I told you that every encoding is a leaf of the binary tree. That is what it means. You have to assign all your encodings to the leaves of the binary tree. If this represents the leaf of a binary tree, if you keep removing this right side numbers, you will reach the parent of a binary tree. For example, S2 in this binary tree is represented as 100. If you remove the right side digit, you will reach this node, which is a parent. If you remove a digit, if you remove any digit from an encoding, you will leave behind your leaf node and go to the parent of the leaf node. Parent of the leaf node cannot be a leaf node because leaf node is essentially childless. A leaf node has no child. So every parent in this binary tree is not a leaf node. Now what I'll do is in this encoding of Sj, I will remove all my previous digits. I will reach encoding of Si. Using the same logic, I can say that encoding of Si is some parent. It is not a leaf node. But I told you that all the encodings are found at leaf nodes. So this contradicts the fact that encoding of Si is at a leaf node. So therefore, encoding of Si is not at the leaf node. So basically, you can't have prefix encodings. You can make your own small examples and see. Because I told if you cut the encodings of Sj, you will end up with encoding of Si. If you cut the right side digits, you will reach a parent. But I'm telling you that you will reach encoding of Si at the same time. Encodings are found at leaf node. Leaf node can't be a parent node. This is a contradiction. This contradiction came because you told that encoding of Si is a prefix of encoding of Sj. So there exists no encoding of Si which is a prefix. So you will not get any prefix encodings if you're using a binary tree. That is the benefit of, I'll just keep this here. It's in rough. That is the proof. That is what is written in the notes. Anyways, so efficiency is something we'll think about it later. That is done. The other, I mean, you can just, if you notice, I can just, the less is the height of the tree, the shorter will be the encoding of each of my letters. Because see here, I mean, okay, we'll come to the next point, then it will become more clearer. The next point is an optimal an, an optimal encoding scheme corresponds to a full binary tree. Encoding corresponds to a binary tree. Optimal encoding scheme corresponds to a full binary tree. Full binary tree means it has each node has either 0 or 2 children. That is full binary. So we'll look at an example. The proof is in the notes. You can just look at it. I'll not tell you the proof. We'll look at an example. The same example. You have A, B, C, D. Now I'll make full binary trees. This is not a full binary tree. Here you have one child. You don't have zero or two children. So I'll try making a full binary tree with four nodes, four leaf nodes. So four. I am making a full binary tree. Some random.
So basically, ಎಂದಾಗದು ಬೇರೆ ಇದು ಬೇರೆ.
This is an extension. Instead of binary tree, I'm using a full
Full
binary
binary
tree. I need still four nodes because my S has A, B, C, D. My message is basically cabbed. I still have three nodes. I can't do this because it won't be a full binary tree. I'll have to. Does it? Is it a full binary tree? Yes. So I'll randomly assign A, B, C, D, 0, 1, 0, 1, 0, 1. So in this case, my encoding scheme will be A 0 0, B 0 1 0, C 0 1 1, D D.
ಇದನ್ನು ಬಿಟ್ಕೋಚು ಬಿ ಕೂಡ ಬಿಟ್ಕೋಚು.
I'll tell you which node shall be assigned which symbol, which leaf node shall be assigned which symbol. For now, I'm randomly assigning them because I'm not thinking about efficiency. D will be 1. So my message will be let me write. My message cabbed will become 0 1 1 0 0 0 1 0 1. Since I used a binary tree, there will be no collisions, no ambiguity. Binary tree is ensuring me that I'll get a prefix free encoding scheme. I'm using a full binary tree so that I get a optimal binary encoding scheme. Why is it optimal? There is a proof there. It basically, see what happens is, see, this is not a full binary tree, no. What I'll do is I will simply cut down this node. If I cut down this node, I can cut down one more node. I'll cut down even this node. If I cut down this, I can simply join this entire thing to this node. By doing this, I will have reduced 1 bit for all of those characters. BCD. My BCD will be reduced by 1 bit each. So it's becoming shorter. The encoding is becoming shorter.
మళ్ళీ చెప్పు.
So that is the idea behind the proof of why full binary trees are optimal. Wherever you find some nodes like this, you
Why
can
are
just
they optimal?
proof is in the notes. I just told myself. So it will help in reducing the size of each encoding of each symbol. But the thing is, now we will think about the efficiency. What if my message was C C C C A B D? Now C C C will be what is it? 0 1 1 0 1 1 0 1 1 0 1 1 0 0 0 1 0 1. This is my C C C C A B D. If it is D D D D A B C, it will just be 1 1 1 1 0 0 0 1 0 0 1 1. If you notice, I have the same message length, but the size of encodings are different. Now, why is this happening? This is happening because if you notice, the deeper you go, the deeper your symbol is in the binary encoding scheme, the longer does its encoding become. So if your depth is shorter, if your depth is small, your encoding will be small. The depth of D is 1, so it has encoding of length 1. Depth of A is 2, so its encoding length is 2. Depth of B and C is 3. It's at, see, you know depth, no? This is level 0, level 1, level 2, level 3. So depth is 3. That's why its size is 3. So in order to efficiently, now we'll talk about efficiency. In order to efficiently assign symbols to each binary node, whichever symbol is appearing more frequently, you give it less depth. That's why in this case, D is appearing more frequently, and when D is given a higher position, like less depth, then the message becomes shorter. The message becomes shorter. But here C is appearing more number of times, but C is given the biggest depth. That is the worst possible case. Then your message will become very big. Let us compare the size of what would have happened if we used normal fixed length encoding scheme. It would have taken n times CL of n is here 4, 4 log 4r. Size of our message is 4 plus 3, 7. 7 log 4 base 2. This is 14. This size is how much? 3, 6, 9, 12, 13, 14, 15, 16, 17, 18. This is more. What about this? Its size is 4, 5, 6, 7, 8, 9, 10, 11, 12. Its size is 12. This is the fixed length encoding scheme. This is when this is our worst case. It takes more bits if I'll write in simple words. High frequency, high depth. If higher frequency symbols are placed at higher depths, are placed at nodes with higher depth, then you will get a bad number. Your message will be encoded using more number of bits. But then if your characters, if your symbols have higher frequencies and if they're given smaller depths, low depth, then your message will become more efficient. So keeping this in mind, you're supposed to use a full binary tree, and whichever symbol is repeating more number of times, you place it at the top. So basically, small depth. This is the algorithm, not the exact algorithm. This is the idea behind using Huffman encoding. As to how is this implemented, you can find the implementation is. I told you the algorithm. How would you implement this algorithm? That depends from person to person. The way of doing this is it's there in the notes I mentioned. It's mentioned under the implementation. I'll just mention how do you implement this in code. We were supposed to do this in lab as well. Implementing Huffman. So the input is basically frequency of characters. Let's say I'll just write in short. Input is frequency frequencies of symbols. You don't need to name them. We can identify each symbol based on the number of times it appears in the message. The other input is nothing. You just have this frequency of symbols. That's it. Using this input, you're supposed to construct this tree. How do we do that? Basically, let's say, okay, let us look at, let's say your message is, let's say, okay, let me give an example. S is A, B, C, D. Your message is C, 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 A, C, C, B, B, D. Let us say this is your message. So, uh, my fraction of A is basically 1 by how many? 4, 5, 6, 7, 8, 9, 10. 1 by 10, 4. Yes, 1 by 10. My FB is not frequency is basically 1. Frequencies are 1. B appears 2 times, frequency is 2. The probability of C is, it appears 5 times,
Mm-hmm.
frequency is 5. Probability of D is 1 again, it appears 1 time.
Algorithm చెప్తున్నాను.
How do you implement it? So your input is basically what? You can either take frequencies or you can take the probabilities. Up to you. I'll take frequencies. Input is basically 1, 2, 5, 1. This is your array. Now what you'll do is, what you're supposed to do is, let's say you have 1, 2, 5, 1. No? Find the least, two least frequencies.
2 ఎందుకు? 2 ఉన్నాయి
No, no, no.
frequencies.
I'm telling you the algorithm.
Okay.
Find the two least frequencies, which is this one and this one, and then join them together. So what you'll get is 1, 1. Join them. Then the parent node shall be the FC6. 4, 5, 6. Oh, this is 6. Thank you. 6, 7, 8, 9, 10. Yes, this is 6.
Laptop will listen video.
I mean, it's fine. It's just a number. So if you add these two, you'll get 2 here. What remain are 2 and 6. Then you find out the next two least elements, least frequency nodes. It is this one and this one. Then you will get 2, 2, 1, 1. If you add these two, you'll get 4, 4. 6 is remaining. Then you take the next two least frequencies, which is 4 and 6. Oh, sorry. So you will get 4, 6, 10, 2, 2, 1, 1. This is the output. This is your output. How is this my output? Because you just have to assign your symbols to the leaf nodes. So any of this could either be A or D. It doesn't matter. This could be D or A. Doesn't matter because they're of the same frequencies. But 2 is basically my D. uh, B, 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 no, B. 6 is my C. So if you encode your message is here. What is it? 4 C's or whatever. If you encode your message, your CCCC, no? Let us look at the encodings. 0, 1, 0, 1, 0, 1. It is a full binary tree. It is. We look at the encoding. You will realize it. Why is this the best way? My CCCC A CCBBD. I think this was the message. Yes. So it will be encoded as 1111. A is 0, 0, 0. C is again 1, 1. B is 0, 1, 0, 1. D is 0, 0, 1. I took this as A. I took this as D. Its length is how much? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Its size is 16. If you used fixed length encoding scheme, that would have been 4, 5, 6, 7, be 10 log. The size of my alphabet is 4. This is 20. If you would have used fixed encoding scheme, the length of your encoding would have been 20. But using Huffman, we reduce it to 16. Why is this happening? Because you have some letters that are repeating for more number of times. That is helping us make this tree. We are assigning it just 1 bit. C is represented by 1 bit.
So అదే algorithm.
This is the algorithm. So this is how you're supposed to implement it as well. What you're supposed to do is you take this as your input, you make some nodes, then you put it, you start making, uh, you have to make a min heap priority queue. I'll just write that here. You make
So basically
from here, you need to make min heap priority queue. It is one thing only. It's not two different things. Min heap priority queue. You are making this min heap priority queue so that you get to get two least frequencies, because in a min heap the root will always be my least frequencies, my least frequency node, so I can always delete it in constant time because it's the root. But then I'll have to heapify the heap again. Now again, see, heap is being used, so everything is described in detail in the notes. You have to go through it. You are supposed to know what is a min heap, what is happening there. It will take require some reading on your own. I'll not be telling that now. So we need to convert this input into a min heap priority queue so that you get two least frequencies every time you ask for it. Then you're supposed to construct these things. You're supposed to construct a full binary tree. That's it. First, you make a min heap priority queue to get two least frequencies. Uh, I mean, see, the procedure is in the notes. You just look into it. After getting two least frequencies, you merge them, merge the two least frequency nodes. After merging them, place them back. Place the parent node back into the min heap priority queue. So after you place it back into the min heap priority queue, you can then ask for two least frequencies once again and repeat the process. Then you will get
min heap lo pettala malli.
this node, the node 2.
Okay.
The node will store within itself the left address and right address. It's a node, no? You can make a struct. You're not supposed to lose information. You make it into nodes, and then you continue the process. Two least frequencies, then you merge them, place them back in the min heap priority queue. Then you get two least frequencies. Finally, when the size of the priority queue becomes 1, it means there is only this one in the priority queue. That means your tree is ready. This is the output. That is the output of the Huffman encoding. That's it. This is the end to Huffman encoding. Huffman encoding is done. After this is interval scheduling problem. It will not take much time. Huffman encoding 10 minutes
Half an hour.
because the proofs and all. I didn't still tell the
Okay, fine.
entire proof. You can just go through it. I mean, you will find a big chunk of text in the PDF that I shared with you guys. I think that should be helpful. Yes, that should be enough, at least for the exam. Huffman encoding. I'm not asking you to buy hard. Just know what is happening and write it in your own words. That is more than enough. Moving on, there is this interval scheduling problem. We will look into it in the next 10 seconds. I'll just wait for a while. Let this sink in. I don't know if it's sinking in or if you're sinking in a ocean of thoughts.
Ocean of thoughts.
Ocean of thoughts. An ocean of confusion. Okay, anyways, let me. The next example is the third.
Ocean of DMS.
An ocean of depressing thoughts.
Very depressing subject.
Depressing subjects. It's too dark. Anyways, interval. Okay, I hope. Interval scheduling problem. Anyways, we'll get on with this. This is the last thing. Then everything will be will अच्छे दिन आएंगे. Nice happy days. After this is done. Interval scheduling problem. Interval scheduling problem is basically that you have many intervals. You have many intervals. These are all the intervals. This is the start time. This is the end time. So you have many such intervals. They will be overlapping with one another and whatnot. You can have many of them. I mean, they could start and end at the same time. So many things are happening. What you're supposed to do is you're supposed to create an algorithm that will ensure that most number of requests are entertained. So let's call this request 1, whatever, request 2, request 3, so on, 4, 5, 6, 7, 8, 9, 10, whatever. You have, let's say, n requests, and each request has a start time. Each request has a start time. Each request has a finish time. This is the start time. This is the finish time. You're supposed to uh, you're supposed to accept, or you're supposed to honor the most number of requests, ensuring that there is no conflict. So let me take a smaller example. Let's say I have something like this. Uh, I mean, if you look at it with your own eyes, you'd probably take you'll let's say, uh, which one will you take? Let me reduce. If you choose this one, you can't choose this one. You can 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 choose this one. That's five ways. Are there better ways to choose? Yes, you can ignore this one. I mean, okay, we ignore that one. You have to ignore this because it's conflicting. You ignore this one as well. You choose this, you choose this, you choose this, you choose this. Okay, it's still five. There's no other better way. Let me do it once again. Let's say you have some intervals here. One, two, three, four, five. Five is nice. If you do one, you can't do this. This is long. If you do this, you can't do this, you can't do this. This is 4. 4 is bad, so we won't do 4. If you ignore the first one, if you do the second one, you have to ignore this. Oh, you're getting 5 again. 5 is nice. Uh, if you ignore this one, if you do take this one, you can't take. Okay, you'll get 5 again. If you ignore this one, you take this one. You have to ignore this. You have to ignore this. Take this. Take this. That's 3. So there are many possible solutions. You have to find the most optimal of them. There can be more than one optimal solution because you've seen it here. You can either take this one, this one, this one, this one, this one, or you could take this one, this one, this one, this one, this one. They are two different solutions, but they have the same number of requests. They are entertaining 5 requests each, so that is the maximum possible requests that can be honored. So this is one example. 5 5 is the answer. Answer is 5. So if you have this interval, the answer should be 5. We have to construct an algorithm that gives us 5. So we discussed various methods in the class. The first method was we would look for the smallest starting times, or earliest, if that makes sense, earliest SIs. We look at the earliest SIs, and then we'll see if this algorithm works or not. Let's see. Algorithm is basically telling that if you find any interval with the earliest starting time, take that, and then ignore the requests that are conflicting with the existing request. So, for example, uh, if you use the same algorithm, what will you get? If you use this algorithm on the same example, you'll get this one. This is earliest time. Uh, this is conflicting. Earliest time, earliest time, earliest time. This is conflict. Oh, let me erase these arrows. Earliest time. This is earliest time, but this is conflicting. Earliest time, but this is conflicting. Earliest time, no conflicts, no conflicts, no conflicts, no conflicts. So 5, you're getting 5. It is working for this example, but let us look for a counter example. I'll give you a counter example that will counter this algorithm. It will say that this algorithm does not always work. So the counter example looks like this. So let's say this is the earliest starting time. So I have this thing. So your algorithm, your earliest starting time algorithm, will pick this, and since all the others are conflicting, it will just ignore all the other requests. Your earliest starting time algorithm is giving you the answer 1, but the real answer is way greater than 1. So your algorithm is failing here. You can't make an algorithm that simply says look for the earliest starting times. That's not right. It's not giving you the right answer. You could have simply ignored the first interval, and then you could have honored the other intervals. That would have been nice. So some people might think of there is another algorithm someone must have suggested. This is not working though. This is not working. The other one is look for shortest interval length. So or shortest durations. Shortest duration. So make an algorithm that searches for the shortest durations and honor all of those. In case of any conflicts, reject those algorithms. Will this always work? Let us look at some example. I'll try to provide a counter example. So shortest duration. No? Hmm. Let's say this is the interval map, whatever you have these intervals. If your algorithm looks for the shortest duration, it will pick this one first, and it will look for other intervals. The other intervals are conflicting with the existing selected interval, so this will be rejected. This will be rejected. So your shortest duration will give you answer 1, but the correct answer is 2. You could have ignored the shortest duration, and you could have honored the two longer ones. So your algorithm cannot be based on finding the shortest durations. So this is also not working. Let us look at the third proposal. Uh, someone proposed that we would look at requests with the least number of conflicts. I mean, someone thought of this. We will look into why this doesn't work. This doesn't work because we look at a counter example. Let's say we have two peaceful intervals not conflicting with one another. Let's say this has many conflicts. Uh, let's see. So the first thing that the algorithm will do is mm, how is this a counter example? 1, 2, 3. Okay, fine. Let's think about this. The answers is supposed to be three, no? You can honor this, you can honor this, you can honor this, and three is the answer. Let us look at what this algorithm will do. The algorithm will look for the least number of conflicts, right? So first it will pick this. Uh, is this a counter example? Let me make another counter example. Uh, mm, or let's say it's like this. Uh, can you come up with a counter example? I can't think of a counter example, but there is a counter example. If this was the case, you okay, fine. This algorithm will pick this first. Next, it will pick what? What will it pick? Mm, okay, so I think this is a counter example. Uh, the answer is supposed to be four, no? One, two, three, four. Four is supposed to be the answer. I think. Can there be more? No, there can't be more. What will the algorithm do? It will look for least number of conflicts. This has least number of conflicts, one. The other least number of conflict, uh, it could either be, we'll take this one. It has, no, it has two conflicts, no? This, this has the least number of conflicts. It has just one conflict. The other one is this one. It has two conflicts. What will the other one be? I mean, no, this can't be selected because this is conflicting with the selected one, so this has to be ignored. The next could be any one of this, but this has to be ignored. This can't be chosen. Okay, here also you're getting 4. Huh? Here also you'll select this, you'll select this. You're getting 4. I need a counter example. I mean, okay, fine, just find the counter example yourselves. Uh, what about this case? Here the answer is 1, 2, 3. Here the answer is 3. Least number of conflicts 1, 2. You can't choose this, conflicting. 2. You can't choose this, conflicting. I choose this. If I join this, here the answer is supposed to be 1, 2. The answer is 2. Least conflicts 1. This can't be chosen. I can't think of a counter example. Just think of a counter example. I'll do that as a homework. Find counter example. Just do it yourself. Apparently, this algorithm also won't work. The other approach is uh, sort it based, or just say you just look for earliest finish times. Apparently, this approach will work. This will not work. Why will it work is a different question, but we will look at how this is implemented. So what you do is your input is an array of requests. So you just your R is basically R1, R2, and so on. And you have n requests, and each request has a start time and a finish time. So what you'll do is you will sort your array of requests with respect to the finish times. So in ascending order of finish times, you will sort your requests. So let's say your sort based on finish times. So if you do that, let's say your sorted array looks like this: some R1 dash, R2 dash, and so on, Rn dash. This is your sorted array. Now what you'll do is this has, so how will it look like? So basically, if you have some intervals, So the first finish time is this one. So this is R1 dash. Next finish time is this one, R2 dash dash. The next finish time is where is it? Here. This is R3 dash. The next finish time is here, R4 dash, and so on. The last finish time is here, so Rn dash. So this is the meaning of this. When you sort it based on your finish times, this is how your intervals will look like. So the algorithm states that you include the interval with the first finishing time, and then you remove the uh, intervals causing any conflicts. So first I'll check R1 dash, I'll check R2 dash. R2 dash is conflicting with R1 dash, so I'll remove it. Is R3 dash conflicting? No. So I will include R3 dash. Now we'll check if others are conflicting. This is conflicting, so this will be removed. Next finishing time is here. Is this conflicting? It is conflicting. Gone. Next finishing time is here. Is this conflicting? No, it's not conflicting. So I will include this. Next finishing time is here. Is this conflicting? Yes, it's conflicting. Conflicting means it's overlapping. So you're not supposed to have overlaps. This is gone. Is this overlapping with any of the selected ones? No, it is not overlapping with any of the selected ones. This will be included. Next finishing time is here. Is this overlapping? Yes, it is overlapping with this one. Next finishing time is, okay, let's say this is finishing first. Is that overlapping? Yes, that's overlapping. Is this overlapping? It's not overlapping. Include this. Is this overlapping? Yes, so this is gone. So here you'll get 1, 2, 3, 4, 5. Here the answer is 5. This is a greedy approach. You will not find any other algorithm that finds more than 5 intervals. You can take any other example. We can look at the example previously. If you apply it in this example, it will look for the first finishing time, which is here. So it will include this one, this one, this one, and so on. So it is this is it is solving this problem. Whatever problem we had in case one, it is solved. In case two, what will it do? It will search for the first finish time. It will include this. Then it will include this because this is conflicting. This is solving the problem we had in second case also. Third case, I don't have a counter example with me right now. So let's look into it. Find a counter example and then apply this fourth algorithm, the earliest finish times. You will notice that it is giving you the optimal answer. The proof or the reason as to why is it providing an optimal answer is given in the notes. It basically says that if your algorithm is greedy and if it is working, it will give you the optimal solution. An optimal solution. There can be multiple optimal solutions. If your algorithm is greedy and if it is working, see, all of these algorithms are greedy. All these four are greedy, but the first three of them are not working. The fourth one is working. Why is it working? There is a proof. You can look into it. I don't think uh, there is a proof in the notes as to why do greedy algorithms when working give you the when greedy algorithms work, they give you the optimal solution. The proof to this is given in the notes. The proof to uh, the reason behind why is the fourth algorithm working, I don't have it. Maybe you could think about it later. Why is it working? Why is this algorithm working? You can just think about the reasoning given in the notes is it is a greedy algorithm, it is working, therefore it will give you an optimal algorithm. The proof to which is given in the notes. The proof to why does the greedy algorithm give you an optimal solution. That's it. Nothing else is left. In the previous class, we started the knapsack problem. So the discussion will be continued in the next class. Sir will be discussing it. So, and if you have any doubts in the DA assignment also, probably sir will uh, like take your doubts in the class and address them. So that's it. There is nothing more to it. I will be stopping the recording now. I hope the recording has been